we gotta start with some basics.
Is that 1.2 or 2.2?
1.2. We're skipping a chapter and
I was going, uh-oh, we're in trouble now.
yeah, I'd like you to read the rest of chapter 1, you know, just kind of get it, and then we'll be on. Suck. Some teachers do that, I've heard. Anyway, no, we're 1.2, my bad. I just like the number 2, so I thought I'd put it up there on the board. See what happens, you know. We're going to have to start with some basics. Some basics that we know are truths, and then we'll be able to figure out some properties, use those properties to discover how to compute some limits. So first little basic here. The limit as x approaches a of a constant c, where c is a constant. What's the picture, what's the graph of a constant? Show me with your hands what the picture of it. Sure, yeah, exactly. What is it? Yeah. What's the picture of a constant? Of a function equaling a constant? Yeah, it's not this way, right? It's this way. That's a constant. It doesn't change slope-wise. The slope is 0. It just goes straight across. True? So if I were to draw the picture of this, you would agree that that would be my function, right? Well, here's the cool thing. If I take the limit at any point whatsoever, so for instance, here's my a. Here's my a. I just picked a random point, doesn't matter what it is, okay, it's arbitrary. What's the limit as we go from the left and the right? Firstly, is it the same thing? Yeah, it's not gapped or anything, it's going to the same thing. What's the limit as we go from the right? What's the y value as we approach the a value? C. How about this way? So the limit is? C. What that means is the limit of a constant is the constant itself. That's cool. Where c is a constant. That's nice, right? That makes sense graphically. We just kind of interpret it. So every time we take a limit of just a number that's a constant, we just have the constant. That makes things nice for us. Number 2. How about the limit of x as x approaches a? So what's the graph of just x, like y equals x? How's that look?
Line that passes through the origin.
It goes through the origin, great, because the slope would be 1 and the y-intercept would be 0. So this is just, if you show me with your hands, how would it look? Yeah, just like that. Not like this, but a diagonal. Now I'm going to pick another arbitrary point A. The question is, if this is y equals x, just our diagonal line, if you plug in a to y equals x, what do you get out of it? Yeah. You get out a, true? You plug in 2, you get out 2. You plug in 3, you get out 3. You plug in 4, you get out 4. You with me on that? So my question is, as x approaches a from the right and from the left, what's the y approach from the right and from the left? It approaches a. So from the right, our function, the y value is going towards a, true? From the left, the y value is going towards a. Does the limit exist? It's the same from left and right, and it's equal to how much? A. Cool. So here's 1. Here's 2. It says the limit, this is really interesting. It says the limit of a like x, just a simple function like this, is the same thing as if I were to just plug that number in. So if I'm taking the limit of some function x at some point a, the answer is just a. That's it. That's kind of nice, right? Why? Well, because graphically we can see that. Last one. Amazingly, with this stuff, we'll be able to do everything else. It's kind of cool. This I'm just going to write it out because we just covered it a second ago. This is why we covered it a second ago. How much is the limit of 1 over x as x approaches 0 from the left-hand side? It was on the board just a couple minutes ago. How much is that? Very good, negative infinity. How much is the limit of 1 over x as x approaches 0 from the right-hand side? What was that? Now, last thing we're going to do today. Firstly, are you okay with these 3 basics? Okay, these two. This one we already knew. These 2 are kind of interesting. They're really unique, and we're going to use those to solve some limits here in just a bit, to evaluate some limits, I should say. Before we do that, though, I got to tell you the properties of limits. We're going to leave it that for today, and I'll show you how to apply these next time. So, some basic properties. We're going to assume that we have 2 functions. And that the limits exist for each one. So the limit of f of x as x approaches a exists. The limit of g of x as x approaches a exists. Notice please, that these limits are, that the x is approaching to the same exact value. You see that? The a is the same. It's got to be the same for this really to work, okay? So it's got to be the same approachment. I just made that word up. I don't know if it exists. But you got to approach the same number. Here's your properties. There's basically 5 things we can do. They're all quite interesting. First one, this is why both of those have to exist, is because we're going to do this. If you have a limit, you're not going to see why this is really interesting until next time, so make sure you come back on Friday. If you have a limit where you have a function inside of it added to another function, no matter what that function is, you can separate that function. So for instance, you can do the limit as x approaches a of f of x plus the limit as x approaches a of g of x. That's legal. You can separate limits by addition. It's kind of neat, right? By the way, this is why you had to have the same letter here, because we have to do that. And you can also combine them. That's legal to do as well. So these are not one-way streets. Let's see. I'm going to make this a little bit easier for us. I'll not write the second one. I just need you to know that this works for addition and subtraction. That makes it nice. It also works for multiplication. You can separate limits by multiplication. So that's legal to do. You can also separate them by division, which means if you have limit as x approaches a of f of x over g of x, that's the same thing as the limit of f of x over the limit of g of x. That's true, but you have to have something. What can't this equal? You can't have that. So the limit of g of x cannot be 0. Last one, the one that I find the most interesting. This is really cool. I know we're a minute or 2 over. Sorry about that. If you have the limit raised to some power, some function raised to a power, this is the coolest one. You're going to see why in next time. But you can actually do this. This makes it so you can do a limit of the function and then raise it to the power. That's a neat one. That means that you can remove an exponent from your function with limits. That's very cool. What's fascinating about this is it even works with this. Because that is an exponent, right? A radical is an exponent. You can remove a radical. I'm going to leave it like that. You can take a radical outside of your limit. We're going to do many examples of those things. But have those written down. We'll start with that next time. Well, if you remember from last time, what we're talking about is limits, and I think the last thing I did leave you with was the properties of limits. And there's a few things that we can do with our limits. Now one thing we knew was that from our basic limits, our little basis up there, the limit of a constant equals that constant. That was real nice. Also, the limit of just a simple variable like x equaled whatever the x was approaching, that number. So those are the two basics that I gave you, and then I gave you some properties. Basically, with our properties, it says you can split up limits by addition. You can split up limits by subtraction. You can split up limits by multiplication. You can also do it with division as long as the limit of the denominator is not 0. You can also, this is the coolest one I think, anytime you have a function taken to a power inside of a limit, you can take a limit of the function and then take the power afterwards. So that means you can really alleviate the problem of having an exponent within any limit. Are you ready to see how we can do that to evaluate that limit without doing those silly, like, check a 2 in the middle and then find out from the left and from the right? You remember doing those, right, those tables? We don't want to do that anymore. We want to use the properties and our basis for limits to be able to solve this thing. You ready to do it? So here's what we can do. If we look at this thing and say, okay, limit as x approaches 2 of this function, the first thing I know is that I can separate limits by addition and subtraction. You with me? So what this says is, okay, well this can become the limit as x approaches 2 of x cubed minus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 7. Now, a lot of people are going to ask, do I have to put the limit as x approaches 2 every time? Yes. Yes, you have to do it. It's like asking someone to take the absolute value. You have to write absolute value until you actually take the absolute value of something. So you have to keep on writing limit until you actually take the limit. If you don't, well, you're saying you've taken the limit, and that's what it was. So then that's not a true statement. So you have to write the limit as you're doing these problems. Now, let's use those other rules. One other rule said that anytime, this is the cool one, the coolest one, rule number, property 5, says anytime you have a function to a power, what I can actually do is take the limit of just that function and raise it to the power later. That's true, you can do that. It means I can take the limit of x and then cube whatever that happens to be. Another thing said that I can separate two limits by multiplication. So this would be the limit of 2 times the limit of x. Plus, that's already a constant. We'll deal with that in just a second. How many people are okay with this so far? Do you see what we've done with these properties? We've actually broken up a pretty intense polynomial into limits of constants and limits of just x terms. Have you seen that? What's interesting is, I want you to think about this, can you do this for any polynomial? You can always separate by addition and subtraction, right? You separate term by term then. Can you always take out exponents? Yes, yes you can. Can you always separate multiplication? Absolutely. So you could do this with any polynomial. You follow me on that one? Well, now check it out. Since we've broken it up into such simple components, you can now use those there's only two basics. Use those two basics to actually evaluate this limit. Can you tell me what's the limit of x as x approaches 2? It was one of those basics that I gave you. I drew the pictures of them. It said the limit of x as x approaches a was a. It said the limit of c, no matter what, was c. You with me on that? So the limit of a constant is the constant. So the limit of x is a, whatever it's approaching. So y'all tell me now, what's the limit of x as x approaches 2? It's just 2. Yeah, 2. And then I can cube it. Minus. Oh, how about this one? what's the limit of 2? Doesn't even matter what I'm approaching, but what's the limit of 2 as I'm approaching 2? The limit of a constant is the constant. So what's the limit of 2?
2.
It's 2. It never changes. 2. Times. How about this one? What's the limit of x as x approaches 2?
2.
It is 2. Plus, what's the limit of 7? No matter what you're approaching, what's the limit of 7? You with me on the 7? It's a constant, yeah? So we had those two basics. The limit of a constant is simply the constant itself. It's a horizontal line. The limit's always going to be the same. It's just 7. Can you add that together? How much is it?
Who's got 19?
8 minus 4 plus 7? Looks like 11 to me. Did you get 11 as well? That means we've just calculated our very first limit without doing tables and without looking at graphs. We're able to do this. Now, can I ask you to do one thing for me, please? Just check this out. Can you go ahead and just in your head or off to the side, take this number 2, plug it in there, and tell me what you get. Can you do that for me? What's f of 2?
11.
Wait, say that again? 11. Did y'all get 11 when you plugged in 2? Wait, that's weird. Is that a coincidence? No, it's not a coincidence, because here's what we can do. Oh, not 2, sorry, 11. It says, well, if you can separate a polynomial into its terms and then its individual components raised to powers and multiples like that, essentially all you're doing is plugging in that number for those spots, for your spots of x, right, for your variables of x. Basically, you can do that here. So here's what I'm going to say. You already determined, I already asked you this, whether this would work for every polynomial. You said that it, would it? Or wouldn't it? Can you do this with every polynomial? Polynomial are things that looks like that. Can you do it for stuff like that? Absolutely. You can always separate them, take powers outside, break it up into a constant times a variable. That means that to find the limit is an important thing. To find the limit of any polynomial, all you have to do is evaluate that function at the point A, whatever that is. This is going to work for every polynomial. So this idea works for every polynomial.
Is point A always given?
Oh yeah, yeah.
And so it's never, it'll always be a given in the, for initially.
Yes, this number is always given to you. Has to be given. Works for any polynomial. In plain, in mathematics, I'll say it in plain English in just a bit. Here's basically what all this stuff says. It says that the limit as x approaches a of some polynomial. Do you understand the notation? The limit of a polynomial, that's a polynomial, as x approaches some number is equal to p of a. What's p of a say?
Evaluate the function at that point.
That's exactly right. It says evaluate the function at that point. Basically, here's what it says in English. To find the limit of a polynomial, just plug in the number. That's what it says. Can y'all do that? Oh yeah, that's great. It says to evaluate the limit of a polynomial, plug in the value. To find the limit of a polynomial, just plug in the value. Which is A in our case. You want to see a few more?
Yes, please.
Yeah. Hopefully you're not like, nah, done. Forget all the hard stuff. Just leave it like this. You want the hard stuff, don't you? Yes. Not really. Yes. limit of x to the fifth minus 3x plus 4 all to the third power as x approaches 2. That's what we're asking here for. Now, the question is, could you, if they wanted you to, could you go through this whole process and do the same thing?
Yeah.
Yeah, absolutely. You could pull out that 3, that power 3. You see it? You can separate all the terms. You can separate out that power 5. You separate the 3 and the x, plug in those numbers in those 2 spots, and it would be essentially just a valuation of that. So, how can we figure out this limit?
Plug in the number.
Just plug that number. Why don't you do that on your own? Plug that number in there, substitute that in there, because we know that the limit is going to equal whatever this function is with evaluated at the point a equals 2. Was it 30 to the third power or something like that? 27,000. 27,000. How many people got 27,000? 20. Is it 27,000? I hope so. Well, not everyone raise your hand. Are you guys okay on how we got those numbers? I need to know. If you're not, then I can re-explain it. But nudge your head if you're okay on how we got those numbers, the 27,000. Yes? So do you see that what we're actually doing is saying, okay, I know this limit is the same thing as evaluation when I plug in the number 2 and then cube it. 32, 3. Yeah, I know I have too many 2's. 32 minus 6, it's like 26, plus 4, that's 30. Take 30 to the third power, and you get 27,000. You follow me on that one? Yes, okay. And that's exactly what that means. Hey, you just evaluated first limit. Don't you feel proud? No? Oh, well, you're gonna.
You get a plaque?
Sure. Eat a bunch of candy, you get lots of plaque. Get it? Get it? That's a joke. Plaque versus plaque. Oh, it's so, whatever. I know. By the way, not all of our limits go to 2. I'm just using 2, so you know. What about that? Now, is that a polynomial?
Yeah.
It can be.
The answer is no. No, that's a rational. That's a rational function. Is it a polynomial? Mm-mm, mm-mm. But could you still do the same basic thing? And the answer is yeah, you can, because of, I think it's rule number 4, or your property number 4, 3 or 4, one of those things, which says that you can actually separate your division, can't you? Provided that your denominator is not what? Will that make the denominator 0? Will this point make that 0? Then you're fine. Then you're fine. You can do that. So because we can do this whole step, this is the limit as x approaches 2 of 4x squared plus 1 over limit as x approaches 2 of x minus 3. Well, now look at it. Is that a polynomial? Yes. Is that a polynomial? Yeah, they're both polynomials. That's a polynomial and that's a polynomial. So this says you can evaluate that by plugging in 2, and you can evaluate that by plugging in 2. The only thing you got to check for is that the denominator is not 0, which we already know, right? It can't be 0 on the denominator. That would be a problem. So do you need to show me this step? No, no. Just plug in the number. If it works, then you're okay. If you have 0 on the denominator, then you're not okay. Okay? Do you get the idea, though? Do you see that we can separate division? Provided that this number does not evaluate that polynomial, make it 0, then that's fine. So we're going to separate that. We don't have to actually show this part. It's just I'm showing you once that it is true, because now it makes it a polynomial. It makes it a polynomial, and we know from here, hey, you can evaluate a limit of a polynomial by just substituting in that number. So therefore, we can do it here. Have you substituted that in yet? So it's going to be 4 times 2 squared plus 1 over 2 minus 3. 17 over negative 17? Notice how here I have to write the limit, here I have to write the limit, here I have to write the limit. As soon as you evaluate, you don't write the limit anymore. Do you guys see the difference there? So yes, you must write the limit until you actually evaluate it. Once you do that, you're done. No more limits. You just have those numbers, but you have to write it up until that point. Question?
Say that x was approaching 3, would you still be able to? You wouldn't be
So
able to
glad
plug
you
it in.
asked that question. Can I answer that in like 30 seconds?
Okay.
Okay, cool. Love those. Don't you love it, like when you're thinking about something and you're going to make your next point because you're a teacher, you know, that's kind of cool, that you want to do. And then someone goes, hey, what about this? You're like, oh, that's my next point. Don't you love that? That doesn't happen to you. It happens to me all the time, which I love that. Actually, it's going to be 1 minute and 45 seconds. All right?
Do you have the time on that sheet of paper?
Maybe. I'm not OCD. How about that one? Is that a polynomial? Please shake your head no. No, polynomials look like this. That's it. That's polynomials. No roots, no denominators. That's polynomials. So this is definitely not a polynomial, but I want you to see what you can do. Do you see that you could pull the cube root out of it? Once you did that, you could separate by division like we did in this problem. So essentially, anything will work provided you plug the number in and you don't have any domain issues. So basically, if you plug this in, it doesn't make that 0, you're fine. And it doesn't make, well, actually, that's a cube root, it doesn't even matter. Cube roots, you can plug in any number, that's fine. So provided that's not 0. If you plug in 1, does this denominator go to 0?
No.
Then you're fine. Why don't you go ahead and plug in 1 and see what we have. Notice I have my limit here. We could do all this work, right? We could separate the cube root. We could do that. We could show that. We could separate my limits by division and show that as well. But you just need to know that we can plug in a number into a rational or any type of problem that we have, provided that we don't have that denominator 0 and don't run into any domain issues. So if we plug in that value of 1, we get the... Do we still have the cube root?
Yeah.
Don't forget about the cube root. How much does that give you? Well, if you're going to say it. How much does it give you? Cube root of 6. Cube root of 6. Raise your hand if you're able to get the cube root of 6. Okay, I'm 10, 12 seconds over. Now, let me show you this problem. Firstly, do you have any questions on the whole polynomial idea, breaking that up? Any questions on what we're allowed to do over here? We're allowed to evaluate limits by just substituting numbers, provided we don't run into any problems. Problems would be 0 on a denominator, or things that don't validate our domain. That would be a problem. I'm sorry, invalidate our domain. That don't invalidate our domain. I think this is now going to answer your question. In every previous problem, we were able to just substitute in that number into our limit because we knew we could break it up into forms of polynomials or basically, because they're polynomials, powers with individual x's multiplied by constants, right? And we could do those limits. That's why we were able to do this stuff, is because we could have shown all that breaking it up and just evaluated constant limits and limits that just had x's and then taken the powers later. The only difference with this one is, if you try to do that, if you separate this by division, the numerators can work just fine. Because you're going to get how much on the numerator? It's a polynomial, right? You get 0. Is it okay to have 0 on a numerator? Sure. Yet on a numerator, yes. Now, what would happen, though, if you try to substitute in this 2 down here? You get 0. The limit of your denominator would be 0. Is that a good thing to have?
No.
That's a problem. We can't ever have that. What do we do?
The top is the difference of squares.
The top is a so wait a second, though. Are you saying that if I do this, I know you all know a difference of squares, right? What's it going to factor as? Are you saying that I should be able to simplify those out of this expression? Well, wait a second. Wouldn't we be simplifying out a domain issue?
You're not actually gonna
Wait,
ever get to that point.
say that again. Say it
You're
loud.
not gonna actually ever get to the point 2 on the graph.
So are we simplifying out a domain issue? No, he's exactly right. Are we actually getting to the point 2? No. So really, this is kind of weird, but with a limit, we're technically not making any mistake here. We're not actually getting to 2. We're not actually getting to that point. So when we look at this, we go, oh, okay, we could just simplify that out. We're not simplifying out a domain problem because none exists, because we're not actually getting to 2. You just can't evaluate the limit by plugging it in because according to this function, yes, you will at that point. That's the difference between polynomials that don't have issues and things like this that do, that have domain problems. If you're trying to find the limit of this guy as you're going to 2, well, there's a problem with that. There's a hole there, right? Do you recognize firstly that there is a hole and not an asymptote here? What was the difference between a hole and an asymptote according to the algebra? Oh, you better know. You gotta know that.
Asymptotes don't factor out.
Say that louder.
Asymptotes don't factor out.
You're right. Asymptotes don't factor out. Holes do factor out. Do you remember that? So if you can simplify it out, that's a hole. If you can't, you have some sort of an asymptote. So in this case, yes, we have a hole. That means that if you have a hole in your graph, can you actually find out where the function is at that point? You can't even do it. It doesn't even exist. So we have to do limits to find that out. But in order to do that, we do have to simplify this function. We can factor, we can simplify, because we're actually not getting to the 2. This is okay. It's okay because x never equals 2. Never gets there. Really close? Yes. So what we can do now is say, all right, then this, according to the limit, is exactly the same thing as that. Is that now a polynomial? Sure. Can you plug in 2? How much are you going to get?
4.
Answer's 4. That's kind of neat, right? Oh, that should be amazing to you. Be like, yeah, we can simplify this stuff out because we're not actually getting there. Therefore, we change these weird-looking holy functions, not because they happen on Sundays, but because, you know, we have this little, and then we can just plug in the number because now it's a polynomial and we're good to go. So if you can factor and simplify, then you can find the limit. Does that make sense to you? That's awesome. A few more?
Okay.
We're going to make them a little bit more advanced and a little bit more advanced. So by the end of the day, we'll have some pretty unique things going on, okay? Now, before you get all crazy and start factoring everything that you see, you might want to just check that point and see if it's even a problem, all right? Because sometimes they might give you that stuff and there's no issue. It'd be like this example. This would have an issue if we were going to the limit of x equals, or x is approaching 3. Wouldn't that be a problem? But we're not. We're going to 2, so there was no problem here. So at least check and make sure you actually have a problem before you start factoring things out. Make sense? So try it. Do I have a problem if I try to evaluate at -4?
Yes.
Yeah, I do. I get 0 over 0, right? That means you should be able to factor. Hey, if you get 0 over 0, I told you this is the property of mathematics. If you get 0 over 0 when plugging the same number, that means x minus that number is a root. That means somewhere over here I can guarantee you're going to have an x plus 4. Because x minus -4 is x plus 4. This will be x plus 4 times something. This will be x plus 4 times something, and then we should be able to simplify out that problem. Why don't you try that right now? Factor that. I want you to simplify it, and then see if you can evaluate the limit of what you get out of that. Should be your quotient, I suppose. Did you factor? Was there an x plus 4 like I magically predicted? I love it when that happens too. So if you were to factor this out, by the way, have you noticed that when you're factoring, you still must have the limit notation? Do you see that on the board? You've got to have limit. Look at, here's a limit, here's a limit, here's a limit. When did I stop using limit? When I finally actually was able to plug in a number. Do you see that? You must have a limit. I will mark you off points if you don't have those limits. If you go, I'm going to write this limit, but not that one, not that one, I'm just going to get my answer. That's not how limits work. If you say you don't have a limit here and you start crossing stuff out and then you magically plug in 2, you've made a domain issue. If you're working with limits, that's okay. So you have to say, I'm working with limits here until you get down to this point. Do you see the point? All right. So we still have a limit. By the way, that's going to be annoying, I know, because you're going to have lots of steps in some of these limits, but you need to do it. We're going to factor. We're going to factor. See anything that simplifies out of our problem? Now, some of you might be asking, well, wait a second. Don't I still have a domain issue? Because if I plug in 3, I have a problem. Don't I still have a domain issue? The answer is, well, yeah, sure, at 3, but are we trying to figure out what's happening around 3? No, I don't care about 3. What point am I trying to figure around? Yeah, so I've gotten rid of the problem. Because as soon as I cross out this x plus 4, now when I substitute in negative 4, it's no longer an issue. Can you now evaluate at negative 4?
Yes.
Let's go ahead and do that. Notice how I've written limit, limit, factored limit still, and now I can put, well, this is going to equal 2 over negative 4 minus 3. I've now evaluated my limit. I don't write the limit notation any longer because I don't have any more variables. As soon as you substitute in for your variable, that is your limit. And we get negative 2/7 as our limit. How many people got negative 2/7 feel okay with this? Is this understandable? You guys are starting to get the concept of working with this stuff? It's kind of interesting, isn't it? What you can do. I hope it's interesting to you. Oh, I already have it up there. Cool. All right. Oh my gosh. What are you going to do first, do you think? But before you factor, don't get crazy on factoring. What are you going to do?
Check.
You're going to check it. Yeah, check the 5. Because if it works, well, there's no reason to factor it. That would just be a waste of time. Probably confuse yourself too. Like, wait, nothing simplifies. Oh no. Now, if you try the 5 here, do you have a problem? Okay. So if you do have a problem, then what do? Now you factor. So if you haven't factored already, go ahead and factor. What's the top one factor as? Plus 2 minus 5? How about the denominator? What do we got there? Oh, minus 5, minus 5. All right. Did you all factor it correctly? All right. Thank God. Good. At least we factored it correctly. Do you see anything that simplifies? Wait, not both x minus 5s? One x. So we go here and here, yes? And what we get out of this is an important example for you to see. You get x plus 2. X is still approaching 5. X minus 5. Try to plug in the 5. What are you going to get?
0.
You're going to get 7 over 0. Is that still a problem?
Yes.
Oh, man. So wait a second. What do you do if you still have a domain issue on this thing? I've now given you 2 cases. I've given you cases where the problem, the domain issue is a hole. Do you see that? It's a hole, and you can get rid of a hole. It's a removable discontinuity, and you can find the limit of that. It's very easy. You factor it, and then you evaluate. Now I've also given you another case where not only do we have a hole here, we actually have, what is that when you can't simplify out the domain issue? That is a vertical asymptote. So now we have this issue. What are we going to deal? How are we going to do that? Well, this is where you're going to use what's called a sign analysis test. Listen, you really do have to comprehend that if you can get a 0 over a 0, like you did over here, you're going to be able to at least factor it and simplify something, right? Sometimes, as I've shown you, it will get rid of the problem area and you can just substitute in a number and be just fine. That happened here and that happened here. Now, do you have to be okay with that one? Now, other times, sure, we got 0 over 0. We factored it, we got rid of what looked like a problem area, and it was. That's like a hole. However, can you get rid of this x minus 5 in any way whatsoever? If you can't, what was that called again? It's asymptote. What you have to do is a sign analysis test. Here's what you do with a sign analysis test. You put the numbers that will make the numerator and the denominator equal to 0. Put that on a number line. What numbers am I talking about here? 5, definitely. 5 because we want to find out what's happening at 5, and that was our problem area. So 5 is going to have to go over here somewhere. So far, so good? Now, what else do we need? Now, -2 is interesting. We don't really need it because really we're looking at this area. However, we need to know what happens between this range. You see, what you're going to do is called a sign analysis test, and that means you're going to find the sign in this interval and the sign in this interval. The only reason why we need this number is to make sure that you pick something in this range. Because if you don't, if you pick something in this range, this is where the signs change from positive to negative. Does that make sense to you? So you have to find something in this little range and this range over here. It could be anything over here. But in this range, it's got to be between these two numbers. That's why we put the -2. We're not taking a limit to -2. We don't care. Really, we don't care. We want to find out what happens at the 5. Is that clear for you? Scott?
Are you talking about like the trig function sign?
No, no, this is easier.
Okay.
There's no trig functions here.
Okay, so I was thinking the same thing. Trig function aside, I'm going, okay, let's see how we're going to get there.
Where's these trig functions coming from? Darn it, I hate calculus. No, there's no trig functions. This is basic. Okay, this is just plugging in some numbers.
Sign as in S-I-G.
Sign, as in I am signing. Okay, sign, like yes,
That's why they were
sign.
confused, like, so
Sign.
it's like a sign.
Like sign. Oh, I get it. Sign like sin. No, we're not sinning. We're signing here. No, we want the sign. Let me write that. Sign analysis. Analysis is another one of those things you can't really abbreviate that well. Analysis. Got it. The sign analysis. That'll go viral on YouTube. That'll be awesome. So again, the reason why you have to have the -2 is because your sign will change in these two intervals. And we don't care what happens here, but we want to make sure we pick the correct number for this interval. We don't want to be picking -3 because it's going to give us the wrong interpretation of what happens around this. Now, you have to know what happens around the 5. And you already said it once or twice before. Is this a hole or an asymptote? It's an asymptote because I can't get rid of it. You follow? So you know for a fact it looks like this. You know for a fact that you have an asymptote right here, right? So you're going to be in one of 4 situations. Watch carefully. You are either going to be going like this, true? Or like this, or like this, or like that. It's one of those 4 situations, and the sign analysis will tell you what it is. Here's how you do it. I want you to take a number in this interval. What's a good number in this interval? Pick 6. You can't pick 5 because, well, obviously you can't pick 5. Pick 6. Plug in 6. And tell me what you get. Plug it in.
Not the original, but the
No,
opposite
no.
of 5.
No, you know what? What you've done here is you've just simplified out a whole. It's going to give you the same exact answer. So plug it in here. What'd you get?
8.
You got 8 because you did 8 over. Wait, what'd you get? 6 plus 2. Oh, right. 8 over 1. 1. So 8 over 1 is positive 8. That's what I'm looking for. I really don't care about the value. I care about positive or negative. What'd you get? Positive or negative? Positive. Make sure you know how to deal with your signs. Okay? So you got a positive. You know what that means? If you got a positive, are you going to be going down to negative infinity or up to positive infinity? Definitely positive infinity because you're doing positives here. You know it's an asymptote already. Somehow you're going to be looking like that. You okay with that so far? Okay. Now, try another number in this interval. Again, the reason why we have the -2 is to stop us from going too far. So what's a number in here?
4.
Pick a better number than 4.
0.
Pick 0. 0 is a great number. It's an interval. So plug in 0. What'd you get?
Negative
2 over -2. So is it positive or negative?
Negative.
Am I going to be going up to meet that other asymptote at infinity? I'm going to be going... I don't really care how the graph looks. Honestly, I don't. I just really care what the asymptotes are, what the function's doing around the asymptote, because that's what the limit is. What's it doing around the number? Do I need to plug in a number over here past -2? No, this is just to stop me. So you got to tell me, does the limit exist, because we're talking about 5, does the limit exist at 5 or not?
No.
If it did, they'd both be going up or they'd both be going down. Okay, if they're like this, then it doesn't exist. But this is how you show that it doesn't exist. You don't just automatically go, I can't do it, does not exist. Okay? Because you could be wrong, all right? It happened before. It does not exist because you showed it with your sign analysis test. So on your test, when I give you a problem very much like this, which I will do, and I ask you to show your work, or I might even say show a sign analysis test, that's what I'm talking about. I need you to prove to me that that limit does not exist. So if they say show the limit doesn't exist, that's it. Okay? If the limit does exist, you'll be able to simplify out the holes. If it doesn't exist, well then you have to show a sign analysis test. Show that you have an asymptote and it's going like that, or some other way that you cannot make those things go together. How many people understood that? What we were just talking about? Good, all right. A couple notes for you, so I'll write this out so you can remember it later. First one. If you get 0 over 0, what that means is you have a common factor at that point, x minus that point. So if you get 0 over 0, what you're going to try to do is factor and simplify. Factor and simplify. 90% of the time that's going to work just fine. That's these examples over here, all right? The other percent of the time, let's say you factored, you simplified, you still have an issue. So that's number 2. If you cannot simplify the problem, okay, if you can't get rid of the problem, if you can't, we'll say it this way, if you can't cancel the problem, because y'all love the word cancel, right? If you can't cancel the problem, that means it's not a hole. If you can cancel the problem, it's a hole. If you can't cancel the problem, that means you have an asymptote at that point. What you're going to need to do is evaluate it with a sign analysis. So two situations. Holes, cancel them. Great, done. Not holes, those are asymptotes. Sign analysis will show you what that does around the asymptote. If they go into the same thing, it exists. Positive infinity or negative infinity. If it's not, then it doesn't exist, and that's the only way you can show that for us. So if you cannot cancel the problem on the denominator, check with sign analysis because the limit might not exist. Because the limit might not exist. How many people feel okay with what we talked about so far? Okay. I'm going to show you a couple more very unique examples. We'll talk about those. Things you really have to know exactly what to do when you see them. So I want to make sure you see them.
I started writing in all caps thanks to you.
You're welcome. My handwriting is so atrocious. That means bad. So condescending what I just did to you. That's horrible. Sorry. It was really bad until I started writing in all caps, and now I have trouble even writing limit like that. Also, my dad was a carpenter and a draftsman, and so he used all caps all the time, so I wanted to be like him. So I started doing that too. He's much better at it. All right, now, we got this situation here. Limit x minus 1 over square root of x minus, oh my gosh. Well, the first thing you try to do is what? Try to plug it in. Do you have an issue?
Yeah.
Now, you have 0 over 0, true? Unfortunately for us, these aren't easy to factor, right? You probably do have some sort of factor out of that, but it's not easy to do. Polynomials are easy to factor, that's fine. But with this, that theorem really doesn't hold that much water because it's not easy to factor that. So, okay, what are we going to do? Any ideas?
Multiply by the conjugate.
Have you ever heard of the conjugate? The conjugate is those two terms with a different sign in the middle. If we do that, that's one way you learn in your intermediate algebra course on how to rationalize a denominator or rationalize a numerator or basically just rationalize out a square root. So if we do that, that might help us. So don't forget the algebra that you know. Sometimes we can rationalize. If we do, we'll rationalize square root of x minus 1. Oops, sorry, plus 1 over square root of x plus 1. You have to use the conjugate though. If you don't, well then you're going to just make your problem worse because you're not going to get rid of the square root. It's going to be within a middle term of your problem. So you have to alternate those signs. You guys okay with that? You sure? So use that conjugate. Now let's see. Of course we have parentheses here. Now I'm going to give you a little piece of advice. Generally, you don't want to distribute, in this case, the numerator. If you were rationalizing the numerator, you wouldn't want to distribute the denominator because ultimately you're trying to simplify out something. Are you with me on that? You're trying to simplify that out. So I'm purposely not going to distribute the numerator unless I absolutely have to if I run into an issue. So right now I'm going to leave this as x minus 1 and the square root of x plus 1. Why? Because I'm trying to simplify stuff. That's why. Now on the denominator, you tell me what do I have to do with this? I do have to FOIL or distribute, so that means every term times every term. Tell me, what's square root of x times square root of x?
Yes.
Now, do you see what happens and why we use the conjugate? If you distribute this, we get x, we get plus root x, we get minus root x. What's going to happen with that? That's why we use the conjugate. And then lastly, you're going to get what? You get x minus 1. Do you see why we don't distribute the numerator? If you distribute the numerator, you gotta mess crap up there, right? You have to refactor. It's not going to be easy. If you don't distribute it, the factoring's obvious. The simplification is obvious. What are you going to simplify? Well, at least I hope it's obvious. Is it obvious to you what you're going to cross out? All right, good. Woo. Yeah, kind of obvious. All right, well, our limit as x approaches 1, notice I'm still writing limit, is this, well, what do we have left? Are you going to have an issue? Oops, that doesn't look like an x. Are you going to have an issue if you plug in 1? It's not negative, it's positive 1, so we're okay. We have no denominator anymore because we rationalized it. It went away because we were able to simplify it. If we plug in 1, what are you going to get? 2. And that's your limit. How many people feel okay with this so far? Would you like to try 1 on your own? Let's do that. I'm going to give you a little bit more complicated of 1. Not too bad. And if you get stuck on it, no big deal, that's fine, but I want you to at least think about it while you're here. This will be where we end today. So limit as x approaches 0 of the square root of 1 plus x minus 1 over x. Are you going to have an issue here? Yeah, I mean, straight up we're going to 0, and that's over 0. That's a problem. So what could you possibly do? Run away. No, yeah, done. No, we're not going to just leave the problem. We can't plug in 0. The only thing you can do here is, what do you think? Can we use that same idea, but only in reverse? Let's try that. Go ahead and do that. Multiply by the conjugate. Conjugates have to have different signs. They have to. It's got to be the same thing on the numerator denominator. It has to, otherwise you're not multiplying by 1, and if you're not multiplying by 1, you're changing the problem. You can't change the problem. Also, one more thing I need you to look up here at the board. When you do this, that sign doesn't change. It's only the thing after the square root. So this stays the same. Did you all multiply by exactly that? Do you see how that is the conjugate? We have the square root, whatever that sign is, and that whatever that constant is. And that's what we have here. The square root, the different sign, same constant. Same exact thing. Why you need the same exact thing? In case you're wondering, well, Mr. Leonard, why don't you change that sign as well? What you're trying to do is multiply this in such a way that you actually eliminate the root. So when you multiply this one times this one, the whole entire root goes away, right? The only time you can do that is if the roots are identical. So you can't have different signs, otherwise they're not identical. Hey, which one aren't we going to distribute here, the numerator or the denominator? Don't distribute the denominator. By the way, I'm saving your lives here. If you distribute the denominator, you're going to have to factor it again. That wastes time. So literally, I'm saving your time, ergo your life. Nice, right? I know I'm such a nice guy today. So on the denominator, I know I'm going to have x and then the square root of 1 plus x plus 1. I'm not going to distribute that. The numerator, yes, you're going to distribute the thing you're trying to rationalize. So if you were to distribute this, why don't you all help me along here? When I distribute this, what's the first expression I'm going to get? 1 plus x. Very good. Okay, and then what?
Minus 1.
So I'm going to get square root of x, square root of 1 plus x, positive. Square root of 1 plus x, negative. That's going to be gone. That's what the conjugate does for you. And lastly, I'm going to get, so this is 1 plus x minus 1. Anything else we can do with that? Anything else? Yeah, combine like terms. What do you get if you combine like terms on the numerator? That's kind of nice because 1 and negative 1. And this is why we didn't distribute the denominator. Because if you look at that, that's what we're trying to simplify out, right? We're trying to get rid of that. 99% of the time, this works out for you. No, I wrote it backwards, but it doesn't matter. Now that you see the x and x as a factor on the denominator, those things are gone. What's on your numerator, please? Oh, 0 is not on your numerator. What's on your numerator? Come on now, people. 1, yeah. When you cross something out, you don't get a 0. You're actually factoring that out, saying x over x is 1, so you have a 1 up there. By the way, please don't make the intermediate algebra mistake of doing this. A lot of people do this when they're just beginning. They go, oh yeah, I crossed everything out, therefore I have that. Is that true? No, you don't have that. You actually have this. If you forget that, what you're going to end up with is the reciprocal of the answer that you actually want. That's not good. Hey, now can you plug in 0 and be okay? Yeah, even though you still have x on the denominator, look what happens. What's 1 plus 0? 1. Square root of 1?
1.
Plus 2?
Plus 1.
I said 2. I was one step ahead of myself. I'll just write on the board. There you go, 1/2. Would you raise your hand feel okay with our limits? Good deal. Now you know, we went a long way today. We now know how to evaluate and compute these limits. Next time I'll show you how to do some piecewise limits, I'll show you some trigonometric limits, and then we're off to a fun start. Did you have fun today? Did you have fun today? All right, so welcome back. We're talking about limits. We're going to start talking about piecewise limits. Now for us, we found out that when we're taking a limit, usually we can cancel out a problem, or if we can't, we'll use a sign analysis test because we have an asymptote. Hopefully you practice that in your homework. Were you okay with that idea? So generally what we're trying to do is plug in the number, plug in where x is approaching. If it works, great, that's your limit. If it doesn't work, well then you have to factor, do something to find that limit. Typically factoring we'll be able to simplify that a little bit, or we found out we can rationalize denominators and numerators if we have square roots. We can do things like that to work around that limit. Now what we're going to talk about today is some different aspects to that. We're going to talk about piecewise limits. I'll show you what you can do with those things. It's going to be kind of nice. You just got to follow me on this. Then we'll talk about trigonometric limits, and that'll end our day. We have a lot to talk about on trigonometric limits. So, piecewise limits. Here's basically the idea when you're talking about piecewise limits. A piecewise, of course, means different functions all mashed together that have different directions for each part of it. You all seen piecewise functions before. Piecewise limit says, what's the limit as we're approaching that interchange? Basically, does it exist? Does it not exist? What does it happen to be? So our idea is we're going to have to take some one-sided limits because each piece is different, right? We're going to take one-sided limits and see if they match up. If they match up, great, limit exists. If they don't match up, then no, the limit doesn't exist. Are you with me on this? I'll give you a real nice way to do this, a graphic organizer. Hopefully this will help you out. And then, of course, if there's questions, man, ask. So let's talk about this. Our idea is we're going to find some one-sided limits, and we're going to see if they are equal. Let's start with an example. Let's say that I give you this. I say that your function is actually made up of 3 parts. The first part says you're going to do 1 over x plus 2 if x is less than negative 2. I say you have a different range. You have x squared minus 5 if we're between negative 2 and positive 3. And lastly, our last little step, we're going to be the square root of x plus 13 if x is greater than 3. Now, because we have a piecewise limit, we basically have, in this case, 3 different functions. That means we can't just look at this thing, hammer at it, one function, and find out what is the limit of any particular place. What I'm going to ask you for is, can we find the limit at 2 and 3? As x approaches 2 and 3. Why 2 and 3? Well, if you look up here, that's the only place that could possibly have an issue, right? Is negative 2, that would have an issue. Everywhere else it's continuous, the limit's going to exist, no problem. Same thing here, that's continuous everywhere. The only problem would be maybe at the endpoints of negative 2 and 3. Here the only problem could be at 3 with that function. So we're going to talk about the limits as x approaches negative 2 and x approaches positive 3. Are you with me on that? So that's our idea here. What we're going to have to do is find our left side limit for each function and a right side limit and see if they meet up somewhere, if they meet up at those points. Now here's the way that I like to do this. First thing I like to do is draw a representation of your graph, of your number line, basically. Just like that. Break it up into the places where your piecewise function's broken up. What are those key points? What numbers delineates our function from the next piece of the function? Where does one function start and one function stop, basically? Negative 2, that's a key point, right? So we're going to have negative 2 on here somewhere. What's another key point for us? Let's call this one function 1, and function 2 and function 3. Can you tell me what function is in this range over here? What function takes over for this interval? Function 3, because it says for any x's bigger than 3, I'm now function 3. Does that make sense to you? So I know that I'm looking at function 3 here. What interval, which function takes over in this interval? Function 2, for sure. And that leaves this one with f1. Let's make sure. X is less than negative 2, function 1 takes over. Do you understand that this is how actually our graph should look? It should be function 1, then function 2, then function 3. And I'll draw this graph for you at the end, just so you see what this really does look like. You with me still so far, though? So here's the idea. If we want to find the limit as x approaches negative 2 and the limit as x approaches negative 3, we don't have to find one-side limits for all three functions, just the two functions that are approaching that number. So for instance, if I want to find the limit as x approaches negative 2, if I'm going from the left, which function am I going to use? Function what?
1.
From the left, I'd be using function 1. Does that make sense to you? Now from the right, as we're approaching negative 2, which function am I using from the right? Function 2. Yeah, that's right. So around this function, I'm going to have a one-side limit from the left using f of 1, the first function. Then I'm going to have a one-side limit from the right using the second function. Does that make sense to you? It's a way to picture this. How about around 3? We want x to approach 3. How about you guys over here? What function are we going to use as we approach 3 from the left?
Function 2.
Function 2, that's right. That's in this interval. How about from the right?
Function 3.
Function 3. We're not using function 1 over here, are we? We're not using function 3 over here. We're just looking around that number, what functions we have. So now, because we have this, gives you a pretty good idea of what your graph looks like, right? This is how you make up your one-side limits now. Okay, so I'm going to take a limit as x approaches negative 2 from the left, a limit as x approaches negative 2 from the right, and I'm going to see if those two things are equal. If those are equal, then we'll have a limit as x approaches negative 2 in general. If not, well, then we won't. Do you all understand the idea so far? Are there any questions so far on the idea? Okay, so let's go ahead and let's try this. What's the specific function I'm going to use for this one? This is negative 2 from the left-hand side. You all said that was function, which one?
1.
Function, well, what's function 1?
1 over x.
Now write that. This one, by the way, is going to be the hardest. The rest of them are easy. How about going from negative 2 from the right-hand side? What function would we be using? Isn't this kind of nice? You can just look at that, can't you? Kind of cool. Look at that one. Now, function 2, what's the actual function 2? So write that. So we said for this range from the left, function 1. This range from the right, function 2. We're going to see what these are. If they're the same thing, then our limit will exist. If they're not the same thing, will our limit exist? Okay, so we have that idea down. Now, how about we set the other ones as well? Let's start talking about as we approach 3. So we're going to need, again, a limit as x approaches 3 from the left, 3 from the right. If they are the same, we'll have a limit at 3. Let's fill out the functions, though. Let's fill out the functions. As we approach, everybody, 3 from the left-hand side, which function are we using? And function 2, again, you said that was x squared minus 5, so we'll write that. How about from the right-hand side, what function are we using? Function 3. What's function 3? I'm assuming your mumbling was square root of x plus 13. Was that what you were mumbling? 13. Okay. Now here's the deal. I'm going to work this side, these ones first, then this one because that one's a little bit more difficult. Let me posit something to you. What I'm going to say is that if a limit exists, a one-sided limit definitely exists. Would you agree to that?
Yeah.
If a limit overall exists, then a one-sided limit will certainly exist. Agreed? So a limit existing is stronger than a one-sided limit existing. Does that make sense to you? Well, here's the cool part about that then. And this, a lot of you were asking, how do I find one-sided limits? Check it out. If you know for sure that a limit exists, then the one-sided limit will exist. Plug in 3. Ignore the from the left. Plug in 3. What do you get? You get 4. Guess what? That's your limit. Why? Because does the limit of 3, does the limit as x approaches 3 exist for that function? Absolutely, without equivocation, because that right there is a polynomial, right? And you know with polynomials, you can just plug in a number unless you have a problem. Well, if the limit at 3 exists, the limit from the left certainly has to. It must. That's a weaker statement. Plug in 3, you're going to get 4. Does that make sense to you? Let's try it next. Again, if a limit exists, a one-sided limit will also exist at the same number. So, ignore the plus for a second. Can you plug in 3 without a problem there? What are you going to get? You're going to get 4. Saying the limit exists, therefore the limit from the right, well, it has to exist. If the limit exists, the right and left side limit for sure exist. They have to go to that same number. That's going to be 4. Now you're able to answer your question. Wasn't that nice and easy? You just plug them in. That's it. Just plug them in. If you can, just plug them in. Nice and easy. Does this limit exist? Why? Yeah. I don't care that they're not the same function. They go to the same value. Limit is 4. Raise your hand if you're okay with that one so far. Kind of nice, right? One-side limits aren't so bad. Piecewise functions, they can get kind of messy. We'll find that over here, but not too bad. Do you have any questions on this? Because I'm going to erase it because I need the room. Any questions on that? Okay, so again, if a limit exists, a one-side limit will exist. Find out your one-side limits. If they're the same, then you limit at that point for sure. You got it. Now let's start over here. Can I plug this into that function?
Yeah.
Absolutely, that's a polynomial. So ignore the from the right. Plug in -2, how much are you going to get? -1. Absolutely, -1. There's the issue, okay? Here's the issue. Ignore the from the left. Can I plug in -2? Aha. So what you're saying is that the limit at -2, you don't know whether that exists or not, right? You don't know. What's that mean? Can you cross out any part of this? Can you factor and cross it out? Okay, so think back. What do you use if you can't cross out a problem? What do you use?
Sign analysis.
The thing you couldn't abbreviate. That's right, the sign analysis thing. You have to use that. You can't abbreviate it. It's going to look funny in your paper. But you have to use a sign analysis here. So if you have a sign analysis at -2, what we care about, what's happening here? What is happening at -2? Do you have a hole? Do you have an asymptote? Which one? Folks, you all should be able to tell them that. You all should know that at this point. If you cannot cross out your problem, what is it? It's an asymptote. So what do you have as you approach -2? It is certainly an asymptote, yes? We just want to know, is it going upwards or is it going downwards? What could you do to find that out? Any value. Any value to the left over here. So plug in -3. If you plug in -3 to this function, are you getting a positive or a negative?
Negative.
Definitely a negative. So am I going upwards or downwards? Like that, right? So here's what you're just finding out. What does this limit? I don't care from the right. Look, why don't I care about this? Why don't I care? Is this the same function on this side of that -2? Is that the same function over there? No. No, we've already taken care of that one. I don't care about that. I just cared about this. So what does this limit equal? Can you tell me? Yeah, as we go towards -2 from the left-hand side, it is going like that. That's going towards where? Mm-hmm. So let me recap just a little bit. What you're doing, you're breaking up your interval. You have 3 different functions in this case. You set up your limits around those breakoffs for your intervals. You'll use left side limits, you use right side limits, and you see if they're the same. Some of them are going to be easy, like what I showed you over here. Others of them, you might have to do a little bit of work. These ones you can just plug in, that one you can just plug in. This one, if you can't cross anything out and eliminate the problem, you've got to use a sign analysis test. Don't get stuck on that. Okay, you're going to have something like this on your test. Don't get stuck on, what do I do? Oh no, I can't plug in -2. What now? Sign analysis test. If you don't know what to do, you don't got to throw things. Jeez. My goodness. You're in luck.
It survived the crash.
You just got that? No, you just got that with some nice marks on it. Congratulations. Don't just get a new motorcycle, okay? Anyway, so this one, yes, you plug this in. This one, well, you can't cross anything out. You have to do a sign analysis test. Do what you know. Don't get stuck on it. If you can't cross anything out, sign analysis. That's only 2 things you got, okay? So we have this. We were able to plug in a number for the left of our interval. That's the side we were wanting. It went to negative infinity. Does the limit exist for this? This is -1, that's negative infinity. Last time I checked, those things aren't exactly the same. So this does not exist. But that, folks, is how you check. You don't check by plugging in numbers, okay, randomly. You check by showing your work like this. This is showing your work. Does that make sense to you? I don't want little tables or anything like that. See, look, the numbers are not the same. I don't care. I want you to show me what this is. Now, the way this graph looks, if you want to see why this doesn't exist, what this thing is a parabola, part of a parabola, that's symmetrical around the y-axis and intersects at -5. It's going from -2 non-inclusively to 3 inclusively. So if you plug in -2, what do we get? -1? Looks like that. And 3, if we plug in 3, what do we get out of that? 4? That's not really accurate, that part. Can't cross 3 and end at 3, but whatever. Then from there on out, we have the square root of x plus 13, which starts at 4 and takes off something like that. And then we have this one, which at this point, I'm sorry, this one. This 1 over x plus 2, if you graph that, that's some sort of descending function that goes like that, at that point. Does the limit exist as we approach -2? No. This is a rough sketch, by the way. Does the limit exist here? Absolutely, because that was closed off. By the way, it's a function because that's not equal to and that is. That's okay. We don't fail that part. This part would have had the open circle around it, but it's filled in by that point. So we have this parabola. Limit exists there? Absolutely. Limit exists here? No. Negative infinity and a value. Raise your hand if you're able to follow that and feel okay with it. Good deal. Are you ready for some trigonometry? I know it's supposed to be Trigonometry Tuesday, but we're a day early, so it's all good.
Was that one of your drinking party idea?
Drinking party? I don't know drinking parties. Kool-Aid. Limits of trig functions. Okay, there's a couple things you have to buy in on for me to do this properly. And the first thing you got to buy in on is that sine and cosine are continuous everywhere. Continuous means you can draw it without lifting your pencil off the paper. Can you draw sine and cosine such that they are continuous? Do you ever lift your pencil off the paper? No, so they are continuous. So first thing, this is going to come up later in our class, but I want to say it now. Sine and cosine are continuous everywhere. True enough. True enough. So, because we can do that, because there are no problems, we can use something that we use for polynomials. You see, polynomials were continuous everywhere. If you think about any polynomial, I'm not talking about a rational function, okay? I'm not talking about denominators, I'm not talking about roots that we have over here. This is a rational function. Clearly it's not continuous everywhere. Negative 2 fails. This is not a continuous everywhere because it doesn't even exist for a part of it, okay? So we're not talking about that. What we're talking about is continuous functions like this one. That's continuous everywhere. You're not going to have a problem, no holes, no asymptotes. Agreed? Sine and cosine, we just said, are the same thing. Therefore, if we have sine and cosine are continuous everywhere, we can apply the same logic and say, then the limit of sine of x as x approaches a is, what do you think? It's not a. It's not a. You wouldn't say this. You wouldn't say the limit as x approaches 5 of x squared minus 5 is 5. That's not true. What would you do to find it?
Plug in
You would plug it in. So to find the limit of this, what did we do? We plugged it in, right? It wasn't negative 2, it's what we got after we plugged it in. So it's not a. What is it?
Sine of a.
Sine of a. Absolutely. Likewise, because cosine is also continuous everywhere, we can do the same thing. Oops. Yeah, that's true. It says that nothing bad happens, basically. That would be something bad happening. Hang on. There we go. That looks a little bit better. What about tangent? What about tangent? So my question is tangent continuous everywhere? Draw a tangent with your hands. How's it go? Looks like you're dancing. Yeah, you're doing that. I should have used that. I went out dancing the other night. I should have used my S-curves. It would have been the hit of the party. Probably not. Maybe. Probably not. Okay, so we got to do a little bit more work. Since it's not continuous everywhere, we're going to have to break this down a little bit. So the limit of tan x as x approaches a. Let's figure this out. Tell me what is tangent. Use an identity. What's tangent? Sure. So we know for a fact that the limit of tangent is the same thing as the limit of sine over cosine. True? Very true. Very true. Now there was one property of limits that said you can separate limits by division. You remember that property? Kind of cool. Let's do it. Okay. So limit of sine, limit of cosine. Do we now know what the, ignore the bottom. Do we know what the limit of sine x is as x approaches a? Sine a, sure. So this says, okay, I've got sine a. What's the limit of cosine as x approaches a? What's sine over cosine? Aha, and you go, yay! What's the one thing I've screwed up on?
Cosine can't be 0.
Say that again.
Cosine can't be 0.
Why can't cosine be 0? That was the one thing, that one little condition about that property. If you remember, it said you can do that provided that your denominator, when you split that up, doesn't ever equal 0. And so we'd say, sure, the limit of tan x as x approaches a is tan a, except at certain points. At certain points, and that's where cosine would equal 0. That specifically is the reason why you get all those asymptotes on your tangent line, is because tangent is sine over cosine. So naturally, if it's sine over cosine and cosine equals 0, you have an asymptote. Remember the asymptote idea? If you can't cross it out, you get an asymptote, right? It works all the time. So that's why we get those asymptotes going on. And those asymptotes occur at x cannot equal, or we will have a discontinuity Because right here, you go, oh, let me draw some purple so you see it a little different. Cosine x cannot equal 0. If it does, you have a problem. Where that happens is every plus and minus pi over 2. So pi over 2, 3 pi over 2, things like that.
Cosine X or cosine A, or both?
Either one. Cosine x can't equal 0. At those points, you could say x can't equal these things. So, or cosine A. Really doesn't matter. Say cosine A. That makes a little bit more sense. Cosine A can't equal 0. If it does, you get a problem. So tangent wouldn't even be continuous at these points. Plus or minus pi over 2, because when you put those into cosine, you get 0. Plus or minus 3 pi over 2, and so on. And you can see this in the domain of tangent. If you look at the domain of tangent, that's why you get those asymptotes. Every pi over 2, remember tangent? Pi over 2, asymptote. 3 pi over 2, asymptote. And so on and so on and so on. And negatively as well. You guys all right with this so far? This is our basics. You guys okay with our basics? Start ramping it up a little bit. You're like, no, this is fine. Let's just stick with this. We're good.
We need to practice this a lot more.
Too bad.
Said you expected this.
I'm sorry, disappointed a lot this time.
There you go. That looks messy enough, doesn't it? How about that?
Yes.
Do this. That's good.
Oh, okay. What in the world? Let's just give up. Call it a day. You ready?
Yes.
No. Screw this stuff. Math. We just watch football. Can't do math and football. They're oxymorons. Mathematical football. Really an oxymoron. Yep. Brain injuries and football, that goes together. Not math and football. It'll work. Okay. What can you do with this? Well, I'll tell you something. You can, this is interesting, but if a function's continuous, you can treat it like a composition. Is cosine continuous everywhere? So what you can do with this is kind of cool. What you can do is say, all right, since cosine's continuous everywhere, you can do a composition. Cosine is continuous. So, by composition, it's actually reverse composition. Look what you can do. You can say, instead of taking a limit of cosine of something, you can actually do this. It's very much like removing an exponent from your limit. You can say, I don't want to deal with that. I want to deal with cosine of my limit. That's legal. Why would you rather deal with that? Have you seen things like this before? Actually, I think I've given you that exact same example so far in this class. You've seen things like that. Can you do this limit? So as long as you can do this limit and don't forget about your cosine, you'll be fine. It's interesting to think that the angle now is a limit. That's weird, right? So cosine of, what are you going to do with that limit? What are you going to do? First, you're going to try to, before you factor, you're going to try to plug it in. I mean, may as well just try that. If you plug in 1, though, you're going to get 0 over 0. What does 0 over 0 tell you? Is factoring going to work or not? Yes, 0 over 0 tells you that. So you're going to factor it. Probably going to work. Now, we've seen one case where it doesn't, where it was a double root. Okay, that happens. But factoring is something you should try first. So we'll have the limit. X goes to 1 of, well, I know y'all can factor. We got x plus 1. We got x minus 1. What can you do now? Sure. What was that discontinuity that we just talked about? Was that a hole or an asymptote in this particular case? Hole. Hole. Sure, because you can cross it out and there's no more problem left. That was a hole. Now, other question, let's see. Oh, I had one more, it was on my mind. Ah, forgot it. Cross it out. Do you have any problems left? Notice how we have to keep writing limit until we actually evaluate the limit. That's an important part of it. What can you do? Can you plug in the number and be okay? So then what we have right here is cosine of, I know I can just plug in the 1. 1 plus 1. What's cosine of 1 plus 1? Cosine of 2. Done. Cosine of 2. We can do 1 plus 1. I like 1 plus 1. How do you feel okay with this one? So we can treat that like a composition.
No, why couldn't we just insert the one with the initial problem? Why do we have to pull the cosine out? Couldn't you just keep writing it the same way and come to the exact same answer?
Yeah.
Would that be still an acceptable way of writing it?
I don't know.
Okay.
Just showing you can do it. Because a lot of people go, what do I do with that? And you go, well, can you still factor it? Can you still cross stuff out? And the answer is, well, technically no, because it's inside of cosine. But as soon as I move the cosine outside, see what we're dealing with now is a limit, and now it's not a domain problem because we're not actually approaching the 1. So yeah, then you can. Does that make sense?
Okay, so moving the cosine out is just a matter of semantics, basically.
Yes, yes, but important semantics, nonetheless. So can you do it? Yes, you can do it. Does that answer your question? All right. Would you like to try one more? The answer is
Only yes.
most of the time, yeah. Unless I'm really tired.
Does it ever change it on the web form? One could always wish.
I don't even drink coffee. Oh man, if I drank coffee, you guys would be in trouble. If I drink coffee that day, it's like crazy. Yeah, so basically, do you actually have to pull out the cosine? Yeah, you can. You can. That's the reason why this is allowed to do it. Do you have to show me that? I don't really care. What it basically says is if you can plug in the number, you can do it. That's what cosine being continuous everywhere says to do. Also says that you can still cross stuff out as you're going through your problem. Because it's a composition, it's continuous everywhere, you can pull that out. Does that make sense to you? So can we try to plug in a number here? Is that okay? Sure, as long as we don't run into an issue, i.e. you plug in something that's not even in the domain, like a negative root, or you have a denominator that's 0. That would be the only issues you have. Do you have an issue if you plug in pi over 2 here? No, actually, if you look at this, that's a polynomial, right? Plus a function that's continuous everywhere. That means you could split that up by addition. We knew limit rules for that. You could do this one by itself, just plug in pi over 2. You can plug in pi over 2 to cosine because it's continuous everywhere, not a problem. So that says that just like other limits that we're dealing with, try plugging in the problem first. If you can, no problem. So that would be 3 pi over 2 squared plus cosine pi over 2. What's all this going to give you? Not as a decimal. Oh, come on. What's pi over 2 squared? You can say pi squared. It's okay. Pi squared over 4. Very good. So this is going to give you 3 pi squared over 4. Are you following me on that? Okay. What's that going to give you? Don't say it out loud. I want you all to think about it. You need to know that. I said don't say it out loud. And let's hold it in. What's 0? Notice how at this point I don't have to write limit anymore. I actually inserted the pi over 2. Do you guys see that? That's your answer.
So once you're no longer dealing with variables, you don't have to keep writing limits. Even
As
if
soon
you
as you evaluate your limit, at that point, no more limits.
So what if you keep doing step after step? You know, because when I write it out, I do this part of the math and this part of the math, and I keep continuing on. But once there's no longer variables, then
Once you evaluate the limit, no more limits. Once you are able to plug in that number, no more limits. Because you've done the limit, right?
yeah, I just kept on my homework. I kept writing it over and over and over again.
Well, you should. You need to write it. I had to write it here. I had to write it here, here, but not here. Because I was able to plug in the 1.
Now, what if we, maybe say we write it too much, are we
Like
going to
here?
deduct on it? Yeah,
There
so
is no
we-
more limit here.
So if we wrote limit in there,
Yes. The whole thing is you gotta know what a limit actually is, right? You gotta know that a limit is what does the function do as you're getting to that number. You gotta know that as you're getting to that number, if it's a polynomial considered everywhere, you can actually plug it in, and that is your limit. Okay, you say, this is still a limit of something. No, it's not. That is the answer to your limit question. But it's, that was a good question, though. I'm glad you brought that up, because maybe other people were confused about that. It's a good question. Ready for something a little bit more interesting? You know what interesting means in mathematics, right?
Harder. Scarier.
It's scary. Yeah, it's a little bit scary. I'm going to show you something. It's kind of cool. It is not my Darth Vader mask. It's pretty cool. No, I'm lying. My parents once told me that I had a stormtrooper mask, but I'd never been able to find it, so I know they're lying. They're like, oh yeah, we bought that for you. It's like when you were like growing up and you asked your parents, have I ever been to Disneyland? Like, yeah. But really it was just a park down the street with some guy named Greg. It's the same thing. That's Mickey Mouse. No, that's Uncle Greg. Okay. Okay. Let's try that. Let's try that. Oh, okay. Let's go through the process of finding a limit, all right? The first thing you try to do is what? Yeah, you try to plug it in. So you plug it in, what's sine of 0? No, sine of 0 is not 1. Sine of 0 is 0. Over how much?
0.
Can you factor sine? Have you ever been able to factor sine in your life?
No.
No. No. So can you factor out anything and cross anything out? Can I just cross out the x and x and get sin? Yay! No, that doesn't work, okay? Sine has to have something next to it. If you do that, you have sinned in mathematics. That's not acceptable. Yeah, you can't do that, so we're basically stuck. There's no way to do this problem, unless you want to just plug in endless numbers. There's no really a way to do this, but we're going to find a way to do it. You ready to find a way to do it? We're use some trigonometry. Here's our idea. Let's see if I remember how to do this in a while. First thing we're going to do, oh yeah, we're going to bound this. We're going to make up a triangle. So, let's do it right there. What I'm going to do is take part of my kind of a unit circle, not really, and make it better. That's better. I'm going to take my unit circle. What I'm going to do is take an arbitrary angle. I can't be specific because, of course, we want this to work all the time. So I'm going to draw that. Now, what I'm going to do from this, I'm going to make up two triangles. I'm going to drop a perpendicular right from here. I'm also going to drop a perpendicular that goes like that. Okay, so let me define a couple things. Firstly, we're going to call x our angle. Second thing, what do I need? I need this. I need that. Now, what I'm going to tell you is if we need to solve for that, let's see. This is going to be our tan x. How far is this distance right here? From here to here. Why? So, would you agree that, stick with me here, folks. Are you okay that x is our angle, firstly? I'm calling this length y. Okie dokie? And this is 1 from here to here. That's 1. Give me the relationship of tan x then. Sine over cosine, yes, in the specific instance with a large triangle. Tangent is opposite over adjacent, true? What's the opposite? Y over 1. 1, because that is the unit circle. Well, interestingly then, y equals tan x. So this equals tan x. Oh, let's see, one more thing. We also need this distance, and we need that distance right there. So let's say, what do we want to do? This coordinate is, what's the coordinate on a unit circle?
Square root of 2 over 2.
Well, that would be for a specific angle. What is it sine,
Sine.
cosine, or cosine,
Sine
sine?
cosine.
Geez, I'm asking you, come on, you gotta know this.
Cosine sine.
Agree? Okay, because yes, sine x is typically y for an inside triangle. What that means is, I'll try not to screw this up too much for this inside stuff. That means that our x for this inside triangle is cosine x. Do you agree? That means that our y is actually sine x. Right? Now, also, what we're going to be doing is looking at this one gives our height, but also this one. That triangle right there. What we're going to be doing is comparing the areas of these triangles. So let me recap just in 30 seconds what we've done. We've gone ahead, we've made up we have 3 triangles. This one just gave us the height. That gave us the height. This would be cosine, but more importantly, this height is sine x. Do you all agree with that one? Furthermore, if I call this y is equal to tan x because of the relationship of x and 1. You guys okay with that one? Okay. Now we're ready to compare the triangles. So we've actually have 3 things going on. I need you to see all 3 things. First we have a big triangle. You see the big triangle, yes? We have a smaller triangle, that's this one. So we have big triangle, we have small triangle, and then we have sector. Do you agree with that? So what we want to do is consider the areas. We have big triangle, we have sector, and we have small triangle. Can you tell me how you find the area of a triangle? What's the area of a triangle?
1/2 base.
Or base times height over 2, yes? 1/2 base times. Let's look at the big triangle. What's the base? Base is 1. Very good. Times. What's the height? Instead of y,
Tangent.
let's say tan x. And to find the triangle, I divide by 2. I need to show a hand seeing if you're okay with the area of a large triangle. Base times height over 2, we have base 1. Height is y, yes, but y equals tan x. So I'm going to use tan x because I want everything in the same variable and all in x's. And then divided by 2. Let's do this small triangle, then we'll talk about the sector. Small triangle, that's this one right here. Not this too small one, but this one right there. Are you with me on that one? It's that one. And that's the big one. Okay. And then we'll talk about the sector in a moment. What's the base of my smaller triangle? What's the height? The height of my smaller triangle? Sine x, not cosine x, right? Cosine x would be sine x would be the height of the smaller triangle because that is actually a point on the unit circle. Do you believe me? So that would be sine x. And then, well, oh shoot, sorry, I'm off one. 1 times sine x over 2. Are you okay with big triangle and small triangle? You all right with that one? Do you know how to find the area of the sector? Area of the sector.
No, what are we talking about? the sector?
Wait, which one of these are we talking about?
This is the sector. Pie slice.
Can subtract the the area of the sector minus the small triangle.
Sure. How do you find the area of a sector?
Use a big triangle.
There's actually a formula for it. It's this. It is your radius times your angle over 2. Radius angle 2. You ready for the math magic? Ready? But you have to buy into one thing. You have to agree that the area of the sector is in between the areas of the big triangle and the small triangle. Would you agree with that? So it goes big triangle, then sector, then small triangle. True. So what we're saying here is that the area of the small triangle is less than the area of the sector which is less than the area of the big triangle. Agreed or not?
Yeah.
What can I do to the 2's? If I multiply all those inequalities by 2, which is legal, what happens to the 2's? 2's are gone. 2's are gone. So what I'm going to do is change this into sine x is less than x is less than tan x. Some basic algebra. Basic algebra. You okay with that so far? Now here's the cool part. What I'm going to do, I'm going to divide each of these 3 things by sine x. Where sine x is positive, it's in the positive quadrant. That's okay. We're talking about a positive angle right here. What that means is that we're not going to change around these inequalities. So then this does that. You still okay with that so far? We divided everything by sine x. How much is tan x over sine x?
1 over cosine. Sine x squared.
Say it again.
1 over cosine.
1 over cosine, because tan x is sine over cosine, yes? Divided by sine, that means you flip, multiply. You're going to be getting rid of those signs. So you're going to get 1 over cosine. We're almost done. Here's what I'm going to do. I'm going to reciprocate each of those fractions. I'm going to reciprocate the 1, this x over sine x, and the 1 over cosine x. What that's going to do is also flip around my inequalities. If you reciprocate that, it's going to flip your inequalities. Does that make sense to you? That's a mathematical truth. So I'm going to have 1 still, because the reciprocal of 1 is 1, is greater than sine x over x, which is greater than cosine x over 1. Did you see this thing anywhere? Do you see it right in the middle? Do you see how it's squeezed between 2 functions? It's squeezed between 1 and cosine x. Does that make sense? Now here's the theorem. It's called the squeeze theorem. The squeeze theorem says if the limit of this goes to something and the limit of this goes to something, then the thing in the middle has to go to that same limit if these are equal. Does that make sense to you? It says I'm trying to take the limit as we go to 0. Agree? So then the limit of 1. What's the limit of the number 1 as x approaches 0? Can you tell me that? What's the limit of 1? Doesn't matter what we're going to, right? The limit's 1. Tell me, what's the limit cosine x as x approaches 0? Now, what do you get of cosine of 0? What's cosine of 0? Cosine of 0 is... It's not 0.
1.
It is 1. Here's what that says. Check it out. This is by the squeeze theorem. It says that right now, if I take the limit sine x over x as x approaches 0, it was squeezed between two functions whose limit was 1 as we went to 0. It says the limit of 1 is 1. It says the limit of cosine as we approach 0 is also 1. What does this limit absolutely have to be? If it's between those two functions, the limit has to be between those two functions. Only they're going to the same number. What's that limit? It has to be 1. It's squeezed. It's saying the right bound is 1. The left bound is 1. Can it be anything different than 1?
No.
No. It has to be 1. Technically, I'm supposed to have these throughout the whole thing. And that's the big punchline for this part right now.
We're not done with these, are we?
No.
Can't do this.
So again, what we just did, we learned one thing about this. We learned last time that the limit as x approaches 0 of sine x over x was equal to, what was it equal to, do you remember?
1.
Okay, and again, for last time, we did not prove the squeeze theorem. We used the squeeze theorem to prove this thing. We bound it between two functions whose limit was 1. Therefore, this was in the middle of it. That limit had to be 1 as we approach 0. So this equaled 1. That's number one thing you got to remember. You got to remember that one. That's going to be in your head, all right? So memorize that thing. When x approaches 0 of this function, you get 1. If x approaches anything else besides 0, well, it doesn't matter. You can just plug that number in. Okay, that's fine. Now, there's a couple of them that we might also want to know. Is there a relationship for cosine, firstly? And is there a relationship for tangent? We're going to look at those today. Then I'll show you how to put everything together and do any limit, well, that's reasonable, of some trigonometric functions. You ready for it?
Yes,
It's no Monday excuses this time. It's not Monday. It's Monday. Monday. No, it's Tuesday. I got you, Tuesday. And Wednesday. Friday. It's Friday. Okay, I can understand that, but no. It's Tuesday today. We're rolling. So, number one thing. Number one thing. Can we find the limit as x approaches 0 of this? One minus cosine x over x. Well, let me ask you the question. Can you just plug in the 0? If you do plug in the 0, what do you get? You get 0, 0. What's cosine of 0, folks? You didn't know that. Cosine of 0 is 1. So on the numerator, you get 1 minus 1. That would be 0, right? And of course, if you plug in 0, x would become 0. You get 0 over 0. That's a problem. Can you factor 1 minus cosine x and cross out the x on the bottom? There's nothing we can do with that. We're going to have to find some way around it, just like we did with this one. Are you ready for it? It's not going to be nearly as time-consuming or mentally consuming as this one was. Okay, this one's actually quite basic. Here's what I'm going to do. What I'm going to do is find some way to see some sort of an identity in here. So what we're going to try to do is work around this 1 minus cosine x. And one thing I can do, perhaps multiplying by the conjugate would help us. Remember what the conjugate is? Just changes, what about that?
The sign.
Yeah, that's it. So in our case, the conjugate would be 1 plus cosine x over 1 plus cosine x. Okay. Well, let's keep this going. Then I've got a limit as x approaches 0. The denominator is now x times 1 plus cosine x. You guys okay on the denominator? I haven't distributed anything, I'm just putting those together for right now. Now, could you tell me, on the numerator, let's do a little work here. What am I going to get if I multiply 1 minus cosine x times 1 plus cosine x? What would you get out of that? Okay, try it on your own. If you can't do it in your head, try it on your own. Distribute it. Foil it out. You know you've got this, right?
Yeah, cosine squared. I think they're the same things, they both different.
You know you've done that. The first thing you should be getting is a 1, yes? Then you're going to get plus cosine x, and you're going to get minus cosine x. Do you see that? What's going to happen to those middle terms? They're gone, so we're going to have 1. And then lastly, you're going to do cosine x, cosine x. Is that going to be a plus or minus? Minus what? Cosine, not just cosine x, cosine. Yes. Oh, now here's the deal. Using your massive knowledge of trig identities, some of you have and some of you don't have right now, to be the brutally honest truth, what is 1 minus cosine squared x equivalent to using the Pythagorean identity? Oh, you do have that knowledge. That's awesome. Very good if you know that. That's right. Because, listen, if sine squared plus cosine squared equals 1, if that's true, which it is true, and if I try to make this out of this thing, that would be subtracting cosine, right, from both sides. If I do that, we make up another identity. We make up the identity 1 minus cosine squared x is equivalent to sine squared x. Therefore, this thing is equivalent to sine squared x. Can you follow so far? Now, we're going to do a little bit of algebraic manipulation. I have gone from this, I've multiplied by the conjugate, I've used the Pythagorean identity in a unique way to get sine squared x. I haven't done much with this at all. I just had x times 1 plus cosine x. You follow so far? Now, because this is a limit, I can split up limits by multiplication, true? So I'll show you every step by step. Watch what we can do here. With our sine squared x, I know that I could make this limit of sine x times sine x. Is that not still sine squared x? Okay. Again, as x approaches 0. And then this thing, I'm not going to distribute that. I'm going to not distribute it for a very specific reason. Check this out. This is the same thing as x times 1 plus cosine x. So I haven't really changed that at all whatsoever. You still okay with this? You sure? Raise your hand if you are, if you're all right with that. Good, okay, basic algebra. Here's the idea. Look at it. Because we can separate limits by multiplication, check out what we can do. I can group together, because it's just fractions, this thing and this thing. Do you see it? Does that thing look familiar? Yeah, so if we group it, then this is going to be the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over 1 plus cosine x. Very brief recap, very brief. We multiply by the conjugate. What that does is create a sine squared x for us. The sine squared x can be split up into sine x times sine x. The x times 1 plus cosine x, we don't change that at all. What we do is we group it in a certain way so that we can use a previously known identity that we have proven. That's okay, we're using something we've already proven. So now we have a limit of x, sine x over x, and a limit of sine x over 1 plus cosine x. It's okay to split up limits by multiplication. I taught you that property. Are you still okay with this proof so far? All right. Can you tell me how much is the limit as x approaches 0 of sine x over x?
1.
Beautiful. We just did that, right? We just did that. That's fantastic. So this is 1 times. Now, what I want you to do is I want you to try to evaluate this limit at 0. Are you going to have a problem with that? Are you going to have a problem? Why not? Why don't you have a problem now? What's sine of 0? Good. Is it okay to have 0 on the numerator?
Yeah.
Sure. Does it make 0 on the denominator? No. Because you have 1 plus how much? 1 plus 1. That's 2. You have 0 over 2. This is 0 over 2. Agree? So how much is 0 over 2?
0.
What's 1 times 0?
0.
Don't say 1. How much is 1 times 0?
0.
What that says to us is we've just proved something else. We now have this identity, that's identity, the first one we did, number 1. This is the second one. The limit as x approaches 0 of 1 minus cosine x over x is 0. Interesting. You know, maybe you can remember it this way. Well, I do at least. I remember it this way. Something involving sine gives you 1, something involving cosine gives you 0. That's kind of interesting, right? Because usually it's, if sine gives you 0, cosine gives you 1, right? If cosine gives you 1, sine gives you 0. It's almost the same idea here. The sine one is giving you 1. The cosine one is giving you 0. It's kind of cool, right? Same sort of relationship. That's how I remember it, at least. Would you like to do the tangent one? Tangent one's even a little bit quicker. Actually, much quicker. Let's try to find tan x over x. Now, could you just plug in the 0? What's tangent of 0? What's tangent of 0? 0 because sine is 0. And cosine would be 1. That would be 0. But now you have it over 0, so you have 0 over 0 again. So we do need to manipulate it. But here's what we can do. How much is tangent as the identities say it is? So sine over cosine. So we could make this that. Are you okay with that one so far? If we do a little bit of work with this, just a little bit, remember this is like x over 1. You're going to, instead of dividing, reciprocate and multiply, true? So this would be the same thing as the limit x approaches 0 of sine x over cosine x times 1 over x. Still true? Still true. Now, all I'm going to do, because of the commutativity of multiplication and what we can do with fractions, I'm going to interchange this with that. Is that okay with you? Just going to flip them. Why? Well, does it matter the order in which we multiply? And this is fractions, right? So I can make everything one fraction, true? So that means I could make it one fraction, commute the denominators, and then split it back up again. So that means I go, okay, that's the limit. X approaches 0 of sine x over x times 1 over cosine x. I've just switched those two things, and that's fine. You can do that because multiplication is commutative, and you can make one fraction out of that by multiplication. See anything interesting? Have you seen that we're trying to get this thing all the time? Because we know what that is. Do you see the sine x over x? We can still split up the limits. So this would be the limit x approaches 0 of sine x over x times the limit x approaches 0 of 1 over cosine x. Interesting, interesting. Hey, now that you have this memorized, I hope you do. What's the limit as x approaches 0? Don't read the board, right? It's right up there. Just kind of, hopefully you memorize it already. Limit as x approaches 0 of sine x over x. What is that? So this one is 1 times, can you plug in the 0 now? Sure, what's cosine of 0? It's 1. Yeah, what's 1 over 1? Okay. What's 1 times 1? You said 1 a lot today, haven't you? That means the limit x approaches 0 of tan x over x equals 1. Just like that. Just like that one did. Interesting. Like it so far? There's basically 3 things we need to know. These are the 3 limits we need to know of. We need to know the limit as x approaches 0 of sine x over x, that equals 1. We know the limit as x approaches 0 of 1 minus cosine x over x, that equals 0. And tan x over x equals 1 again. If you know those limits, you can break down all the ones I'm going to give you into those 3 identities. If you can do that, this is very easy to master. But it involves some thinking outside the box in certain cases. Would you like to see some examples of how to do that? Okay, let's start over here. Just memorize those 3 properties of limits, all right? Those are the proofs that we just did. Also, I'll say it's got to fit those pretty darn perfectly in order to be true. All right, so let's start with some examples. You're going to see some interesting mathematics. This is kind of thinking outside the box. We're trying to make these things fit in the format that I just gave you, okay? One of those 3 formats of limits. We'll start there. Now, firstly, is this exactly like the limit that I gave you? What's different about this? 2 is a problem. 2 is a problem. What we need to do somehow is we need to make the inside angle the same thing as the denominator. So for instance, if I have a 2x inside my angle, I need a 2x on the bottom of my fraction. Are you with me on that? You gotta have that. Otherwise, it's not exactly the same. You can't do that limit. I'll show you how to do this in just a second. So since we have this, maybe we can do something a little bit special. The only thing we can really do is multiply by 1, right? That's it. Otherwise, we change the value of the limit. But maybe we can multiply by 1 in a special way. For instance, what if I said, you know what? I want to multiply by 1, but I'm going to make it 2 over 2. Is that legal to do? Okay, let's see what we can do with this thing. Now, you can put the 2's anywhere you want to, provided you don't change this. A lot of people, when they're first starting out in trigonometry, hopefully this is not you, they go, well, let's just pull the 2 out front. Wouldn't that be easy? No, you can't do that. You can't do that, right? That is 2x. You can't change that unless you use an identity to do that. The double angle or the half angle or whichever ones that you can manipulate. Those are the only ways you can change your sign of the inside of the angle, okay? You can't just pull out that 2. It doesn't work. But we can choose to put these 2's anywhere we want. So what I'm going to do is I'm going to say, all right, let's be smart about this. Now this 2, maybe I put it in front of my sign. But this 2, let's make that 2x. You okay with that so far? You see where the 2's went? Now, here's something cool. Do you remember that anytime I have a function multiplied by a function, I can split off the limit of that function? We've done that a couple times right here, right? We did that. But with a constant, the limit of a constant is always just that constant. Let me explain that again. When you have a limit of a function times a function, you can break it up. The limit of a constant is always the limit. I'm not teaching anything we haven't had before. What that says in plain English is you can always pull out a constant to the front of a limit. Because the limit of a constant is that constant. Are you with me on that? So basically, pull the 2 out. That's what you can do. That 2, right here, I can bring that out front. So 2 times this. Now some of you might be thinking, well wait, Mr. Leonard, why didn't you also pull this 2 out? Why didn't you do that? Well, if I had, what's 2 over 2? Then I'm right back to where I started, right? That would be silly. I'm doing this on purpose so that I can make these 2 things look identical and multiply it by the number that's basically just left over. Raise your hand if you can follow that, feel okay with it. All right. Now here's a cool deal. How much is sine of 2x over 2x? Do you know? How much is sine of limit of sine of x over x as x approaches 0?
1.
Now here's why this is also 1. You could actually make a substitution. Check it out. I'll show this only one time, just so you see it once. But let's make a dummy substitution like u equals 2x. You okay with that? Tell me something. As x goes to 0, does u also go to 0? Yes. Yes, it does. Because if you plug in 0 here, you get a 0 there as well, right? That means you can make the substitution for the limit. So if I make this substitution, then this limit now becomes u is going to 0, sine of, well, instead of 2x, I put u. Instead of 2x, I put u. Do you see how that now fits our identity perfectly? You can do that provided your bound or your variable still goes to the same spot. It's still going to 0 because when 2x is 0, u is also 0. It's still going to the same spot. Does that make sense to you? So we can do this. This goes, oh yeah, this is 1, therefore this is 1. That's our substitution. It's kind of neat. So then we have 2 times 1. What's our limit? How much? 2. 2. And it's 2. Can you almost see it though in the original problem? Sine of 2x over x. How much is it? Not 1, it's 2. What's inside the angle besides the x? 2. Interesting, isn't it? Are you ready to make these a little bit more advanced, Start building them up a little bit? This was very basic, very, very basic. We're going to start incorporating some other ideas in here. So how about, just little by little though, don't worry now. But I got to warn you, I'm going to cut out some of the steps I've already covered in the class. So for instance, I'm not going to ever show you the squeeze theorem for sine x over x anymore because we've already done that. I'm probably not going to show you this whole routine for getting that answer anymore. Does that make sense to you? Probably not going to show that to you anymore. Maybe once more. But after that, I'm just going to assume that you can see that and that you can get there on your own. Is that fair? I hope so, because that's what I'm going to do. Oh, well this is kind of nasty. Does this look like any of our identities so far? We only got 3 of them. Does it look like any of them? You got to make it fit one. You got to make it fit one of those. Which one's it's closest to? The tangent one, the cosine one, or the sine one? It's closest to the sine one. But I need to have sine over an x. True? Okay. Is there anything we could do? Specifically, can I multiply by 1, something on numerator and denominator, that's exactly the same, that's going to give me something over x, something over x. Stumped ya. Remember that you can incorporate new variables as well, provided that you multiply or you divide and gives you 1. I want this thing over x and this thing over x. That's what I want. Can you make it happen here? X over x? Close, very close. So we know we're going to need to incorporate another x. You agree with that, right? Somewhere the x is going to have to happen.
1 over x.
Oh, okay. So if I multiply by just an x, I get x sine, right? I don't want that. I want over x. How we get over x? Say it again.
1 over x.
How about 1 over x? Is that legal to do? Is this still 1? Okay, let's see what that does to our problem. If you multiply sine of 5x times 1 over x, you're going to get sine of 5x over x. Are you okay with that algebraic step? What's this one going to be?
5.
So we're multiplying in such a way that we can find some resemblance to an identity that we already have. Here we've chosen to multiply 1 over x over 1 over x, which is legal to do because this is basically just 1. It's just 1. We're doing it so that we get sine x over x. You seeing the point here? You sure? Now, are you going to be able? Were you able to think of that on your own? No, but now you can use it, right? Now you can use it in some of your problems. Hey, using what we found out here, can you tell me what the limit of this thing is going to be?
5.
Why is it 5?
It's going to be 5 times the limit of sine x over x.
Could I do the same thing here? Remember, I can separate limits by division, right? So I can write limit over limit. I can do that. So if I multiplied 5 over 5 like I multiplied 2 over 2, ultimately I'm going to have 5 times this limit, where the 5x and 5x is the same. I'm going to have 6 times this limit, where the 6x and the 6x are the same. I'm going to have that. If you want to see it for the last time, this is what it would be. You'd say, oh, okay, let's do 5 over 5. Let's do 6 over 6. I'm going to do a couple steps at once right now. I'm going to break those limits up. I'm going to say, okay, I want the limit 5 sine 5x over 5x. I want limit 6 sine 6x over 6x. Can you make it that far? You guys all right with that one? Yes, no? What can you do? What can you do with this 5 and with that 6? What can you do with them?
Take it outside the limit.
You can, because they're constants, and we know that the constants really don't affect the limit, because you can separate it by multiplication, and you'd be okay. This is all multiplication. That's great. So this would be now 5 times the limit sine of 5x over 5x as x approaches 0. Notice how I'm still writing the limit. All over 6 times the limit as x approaches 0, sine of 6x over 6x. Do you see what we've done? We've basically put two ideas together. We put this idea that I need sine x over x. We put this idea that I can multiply by some constants and manipulate them in order to get my exact identity out of that. Now, I'm not going to show you the substitution again. Basically, I want you to know that a substitution is possible in these cases. How much is the sine of 5x over 5x? How much?
1.
This is 1 right here. This limit is 1. Whenever your angle matches your denominator with that sign and your limit's going to 0, that angle or that limit is 1. How much is this limit right here?
1.
So you have 5 times 1. You have 6 times 1. What's your answer?
5.
5/6. That's right. Raise your hand if that made sense to you. You're okay with that one? All right, good. You want to try a few more? It's kind of fun. I like them. Teach you a little bit about trigonometry, won't it? Or at least refresh your memory about some trigonometry. And learn some things you can do with limits, which are pretty cool. Ooh, let's see about this. Does this look similar to one of our limits that we already knew how to do? Is it exactly the same though? What's different about it? It's got an x squared. Now, again, can you change the inside of your limit? Or, I'm sorry, the inside of your sign. Can you change the inside of your sign? So basically, can I change the x squared? Never. Can't change that thing unless you use identity. That's the only time you can do that. You can't just say, I think I'll pull an x out and put it there. No, you can't. No, you don't. What you want to do is make it so that, if you haven't noticed this in the previous two examples, make it so this angle matches your denominator. What do you need to multiply by to make your angle match your denominator? Because that's what we did here. Multiply to make your angle equal to your denominator. Multiply to make your angle equal to your denominator. That's where the 5 came from. What do you need to multiply by here? X over x would work. So keeping with what we know, this x, I can't do much with that besides put it out in front of my limit. So right here I'll do, okay, I'm going to put that out in front. But these two, yes, that's what I want. Because what I want that angle and that denominator to be exactly the same. You all right with this so far? Now, because limits are separable by multiplication, I can say, well, this is just multiplication. I can separate off a limit of x. So this would be a limit of x as x approaches 0 times a limit sine x squared over x squared as x approaches 0. Hey, tell me something. What's the limit of x as x approaches 0? It's not x. 0, because you plug that in, you get 0. Times, what's the limit of sine x squared over x squared as x approaches 0? 1, yeah, because you could make that same substitution like I had on the board earlier for a dummy variable equals x squared, right? And then as x squared goes to 0, so does that variable, and so does this variable. It would be like a u would be going to 0, as these two things also went to 0. That matches our identity perfectly. This goes to 1. And as I've said, anytime your angle matches up with your denominator, you can do that.
So as you pull out that x, it has the limit as x.
Absolutely.
Because it's not a constant.
It's not a constant. Yeah, the only reason that's a great point. The only reason why we were able to pull this constant out and leave it as a constant is because if you did this, watch this, if you did the limit as x approaches 0 of that constant, what's the limit of 2? No matter what you're going to, right? That's why we can do it. Okay, let's continue on with this. What's 0 times 1? Our limit of x squared over x, sine x squared over x as x approaches 0 is 0. We'll try a few more of these. I really want to make sure you get a handle on this because there's a lot of different combinations of problems we can do. So I'm going to give you as many as I can in the time that we have. That way you feel a little bit more comfortable on your homework. You ready for them? So again, some other examples. Hey, by the way, is this the same thing as this? No. This is the same as that. Sine of x squared is the same thing as sine squared x. What's sine squared x mean? Good. Maybe you can see where this is going. So that's true. You're always trying to break it into limits you know, limits you understand. What's the limit of sine x over x? 1. This is going to give you 1. What's sine x? What's the limit of sine x as x approaches 0? It's 0, because when you plug in the 0, you get 0. So this is ultimately going to be 1 times 0, or 0. This limit, if I'm not showing you a step right here, I'm not actually breaking them up. But if I were to break them up, the limit of this would be 1, limit of this would be 0, 1 times 0 is 0. Ew, that one. Now we're going to talk about this. I'm not going to prove it to you why it doesn't exist. You can get there on your own, or you can look. I think the book has a proof in it. It's pretty good. I'm going to do this graphically just to show you what this looks like. Now, of course, sine is an oscillating function, right? It goes up and down, up and down, up and down. 1 over x, as you get close to 0, goes to infinity, right? It goes there very fast. So what happens with this graph? It looks like this. Sure, it tops out at 1, and it tops out at -1, because sine is bounded in those ranges. This looks something like this. Starts off nice, it goes down, it goes up and down and up and down and up and down. And as it gets closer, it goes faster and faster and faster and faster and faster and faster and faster. So a bunch of crap happens. Right? It's going by the end, by the time it gets to 0, it's going like that. Does it ever get to 0?
No.
You tell me, can you plug in 0?
No.
Then it never gets there. It's undefined at that point. You can't do it. You cannot do it. So it just goes nice and slow and then faster, 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 until it gets nowhere. The other side looks like this. As we get closer to 0, are you approaching a certain point? Or is it just continuing to oscillate like that? It's not actually reaching a point. It's not gonna ultimately go, oh, I'm gonna level out and make 0. Or I'm gonna level out and make 1. It's not doing that. As you get closer, it's still oscillating even faster and faster and faster. By the end, it's just crazy, all right? You can't see it. It's going so fast. So, is the limit gonna exist? The answer is no. No, it doesn't exist. That one does not exist. Sine of 1 over x does. If you ever see that, just sine of 1 over x, that doesn't exist. Okay, so question. This is an interesting question. If that doesn't exist, does that exist? Does that exist? Oh, as we approach. Let me get my white cat and smoke it. You see that commercial with that creepy guy with the white cat? I don't know what that was. Yeah, it was, but it was like on the Super Bowl. I think it was CeeLo. You know who CeeLo is?
7 commercials.
I was forced to watch The Voice last night. That's the only reason why I did. Forced. Yeah. Not like handcuffed or anything, but like it was on, and of course, if it's on, I have to watch it. So there it is. Anyway, does that exist? Let me show you something. Again, we're going to use the squeeze theorem. Are we going to prove the squeeze theorem? No. No, we're going to use the squeeze theorem. Check this out. This is interesting. Do you agree that... Oh, by the way, I did make a mistake on the previous squeeze theorem, using the squeeze theorem. I was supposed to have the equal signs underneath it. I neglected that for some reason. I don't know why I did that. But with your squeeze theorem, you do have to have those symbols, not those symbols. I think I said it towards the very last bit of the proof. I said, you know what, I'm supposed to have these everywhere, but I don't know if you caught that. Let's use some of our knowledge about sine to create some bounds on sine. Forget the 1 over x part for a second. What's the maximum value you can attain with sine? What's the highest sine goes? 1. What's the lowest sine goes? So you agree that's true, right? True? Okay. Well, check this out. I'm now going to create this in here by multiplying all 3 of these sections by x. Is that legal to do? Sure. Yeah. So if I multiply by x, actually I think Yeah, I do. I want the absolute value of x because I don't want to change those signs, so I'm going to make sure I multiply by the absolute value of x. Okay, so here's a slightly better interpretation of what's actually going on in the problem we're working on right here. We're trying to work on the limit as x approaches 0 of sine 1 over x times x. Now, of course, we know that sine is bound between 1 and -1. Sine doesn't get any bigger than 1, doesn't get any less than -1. So we can go naturally make this inequality. Any sine function is between -1 and 1, including sine of 1 over x. So we have that down. Can't get bigger than 1, can't get less than -1. Now, the way we make the jump from here to here, which in class I have absolute value around this x, and I said we can get there by multiplying this absolute value of x, and this absolute value of x, and this absolute value of x, which is true, but it doesn't quite give us back exactly what we want, which is x without the absolute value. How we get there is just by a little bit of rational thought. So we say, if we multiply by x in all three spots, what could potentially happen is, if I don't have these absolute values, I could get a negative number over here, which wouldn't be an upper bound. So what we're saying is, let's make this one absolute value of x. That way we know that that's always going to be positive. No matter what I plug in, I have a positive x. Well, that's certainly going to be bigger than x sine of 1 over x. If this is true, then this has to be true where x is positive. Also, if we let x be negative, we're going to have a lower bound. Now, if I don't have this absolute value, what that says is that negative times a negative could actually get me a positive. I don't want that to happen. I want a legitimate lower bound. So that's where the absolute value is coming from. That says, all right, well then x sine of 1 over x certainly has to be bigger than that negative number. If this inequality is true, then this one also has to be true, and that makes our double inequality here. From there, it's a simple matter of limits. We say, well, we know the limit as x approaches 0 of the absolute value of x, that's going to 0. We know that that's that v-curve as we're going from both sides. The height of that function is getting down to 0. So that limit exists at 0. Same thing, the limit of negative absolute value of x, that's negative absolute value of x. We're going up to a height of 0 from both sides. That limit's 0. So we have the limit of this function is 0. The limit of this function is 0. Since we've now squeezed our function we wanted to find out, this one, since we squeezed that between two functions whose limit is 0 as we approach 0, by the squeeze theorem, we can now draw that conclusion. That's how we get the limit as x approaches 0 of x sine of 1 over x equals 0.
Does the limit only exist because you have an x in front of this sine 1 over x?
Yeah.
Okay.
And which is interesting, because that x right there in front of it allows you to bound it between two numbers and then use that fact to say the limit of this goes to something, the limit of this goes to something. The problem is, if you look at this one, just the -1 sine 1 over x less than 1. Where's this limit go? Where's this limit go? Are they the same? Then you haven't squeezed it. That's the problem. We needed that x to say, okay, by multiplying by, well, the absolute value of x, which is a small point, but multiply by the absolute value of x, the limit of the absolute value of x, yes, that is going to 0. And the absolute value of x, yes, that is going to 0. That is what actually squeezes it. That's the point. Without the x, you can't do it. It fails here. It doesn't work here. It works here. This is another one that we can use. Limit of x, or sine 1 over x, that does exist. It actually equals 0. It's an interesting thing, just by having that x in there. So our whole idea for this is you're trying to break up these limits into the identities the limit identities that we can work with, the ones we already know. That's the sine x over x goes to 1, and the 1 minus cosine x over x goes to 0, and the tan x over x goes to 1 again. That's what we're trying to do. I think I have 3 or 4 more examples. Would you like to see some of the things that we can do? Okay, I'm gonna have to kind of paraphrase these for you because I just want to give you the head start on them. Some of these are in your homework, as a matter of fact, I think. But I want to give you some key points so that you can do these on your own. So I'll be moving kind of quickly. Follow along. If you're not quite getting to see me in the math lab, I'll be there often or my office hours, or check out these videos again later on, see that you can follow these on your own. You with me on that? So a couple of things that we can do. This is basically just practice at this point. You've learned everything we need to know. Okay, while this looks kind of nasty, I want you to see that we can actually do a lot of fun things with this. Firstly, do you see how we have a few cosines up there? We're probably going to be moving towards the cosine limit that we learned about. So if we do that, well, what I want out of that limit is the 1 minus the cosine, true? Over x. I've already got the over x, but I don't have the 1. However, what I can do with that number 2, can I separate that into 1 plus 1? Is 1 plus 1 the same thing as 2? Sure. So then this is really, check out what I'm going to do. I'm going to say this is really 1 plus 1. I'm going to reorganize this stuff then and say this is the limit as x approaches 0 of 1 minus cosine 3x plus 1 minus cosine 4x all over x. Does that work for you? Is that still the same exact thing? Just reorganized it. Now what's cool about fractions is that if you have a common denominator, you can add them, right? And subtract them. What it also means is you can pull them apart by that common denominator. So what that says is, I can actually make this 1 minus cosine of 3x over x. Well, there's one of them. But now I have the common denominator plus 1 minus cosine of 4x over x.
Wouldn't those be different limits though? I mean, you're adding them together?
We are adding two different limits right now. We're not there yet. But that's a good point. We can split up those limits by addition, right? So we now have two different limits. Oh, now. What can we do now? What can we do now? We can do that. What we want is the angle to be the same as our denominator. So if we do that, if we do the 3 over 3 thing and the 4 over 4 thing, move those numbers out front, don't affect this 1 minus cosine of that angle, then we'll be okay. Then that's going to allow us to do that substitution just like we did for the sine. Did you follow that? So we want 1 minus cosine of an angle over the same angle, basically, down on the denominator. That's what we're looking for here. So if I multiply this by times 3 over 3 times 4 over 4, all this becomes is 3 times the limit x goes to 0 of 1 minus cosine of 3x over 3x plus 4 times the limit 1 minus cosine of 4x. It's hard to draw. Over 4x. So we do the same exact idea that we did for our sine. Only here, can you tell me what's the limit as x approaches 0 of 1 minus cosine of some angle over that same angle? How much is that?
0.
That's the 0. So we have 3 times 0 plus 4 times, what's that one going to be?
0.
We do that substitution again, just like we learned for sine. So 3 times 0, 4 times 0. What's the answer?
0.
0.
Do you know that word?
I know, right? All that time spent and nothing. 0. You should have seen the looks on my Math C kids when I did a whole problem using rational functions. Took about 10 minutes, and then the solution didn't work out because it made the denominator equal to 0. And they're like, wait, There's no solution. Like, yeah, isn't that exciting? They're like, I hate you. Oh well. Okay, other things you can do. This is very similar. Now understand that we were able to break up these fractions because we had that denominator. We can do the same thing here. So we could actually make this limit as x approaches 0 of x squared over x minus 3 sine x over x. You guys okay with that one? We can do things like that. We can split up our limit using our algebra. How much is x squared over x? So we'd have a limit as x approaches 0 of x minus 3 times sine x over x. Tell me what happens here. Tell me what happens. Where does the x go to? 0. By the way, the reason why we can do that is because we're not actually getting to 0, right? We can actually cross out the x and x. That's okay. So what's the limit of x as x approaches 0?
0.
This is 0 minus. What's the limit of 3? Is the 3 going to change? Now, you know I'm skipping steps here, right? You know that technically what we're supposed to do is separate these by subtraction, then separate these by multiplication. But we found out that earlier with our polynomials, if you can plug it in and you know the identities, then you're going to be okay. So here, this goes to 0. This 3, that's going to stay at 3. What's the limit of sine x over x as x approaches 0? What's my answer? Answer is -3. Would you raise your hand if you're okay with this one? We'll practice a couple more next time. I want to show you 2 other things we can do, and that'll wrap it up. So we're still learning how to do some problems involving trigonometric limits. So when we deal with these limits, our basic idea is you want to get it down to one of those 3 identities that we knew for limits. Namely, sine x over x as x approaches 0 goes to... Oh boy.
1.
1, very good. Okay, somebody else. 1 minus cosine x over x as x goes to 0 goes to 0. And tan x over x? Oh, good. All right, you got that one. That's the one we don't use that often either. Oh, nuts. Okay, so basically we're trying to get those things in these problems somewhere or another. Now, oftentimes you'll have to use some sort of an identity to do some of these things. So for instance, when I look at this top example, t squared over 1 minus cosine squared t, if I plug in the t, I have a problem because I have 0 over 0. Do you see the 0 over 0? That's a problem. But is there a way I can manipulate this in such a way to get rid of the 1 minus cosine squared t? That right there, at this point, for you who have taken Math 2 or trigonometry, that should be going, oh yeah, I know what that is. What's 1 minus cosine squared t? You need to know. That's sine squared t. Very good. So I can change that. Now at this point, there's a couple ways to go about doing this problem. One option is, do you see how I could break this up? T times t, sine times sine. Do you see that? You could have t over sine times t over sine. You with me? You could break each of those up as different limits. Each one of those limits would be going to 1. I didn't say this to you, but it should maybe have been apparent to you from the squeeze theorem that this limit is also equal to 1. Was that apparent to you as well? That's the same thing. That's the same thing. The reason is because when you do the squeeze theorem, instead of reciprocating, if you left it alone, you have that already. That's in there when we proved it with the squeeze theorem. Also, I can show it to you this way. Do you remember that if you take out an exponent or you reciprocate a fraction, you can actually have a negative exponent? Some of you are zoning out already. Let me show you what I mean. Maybe let's make more sense. If I flip these around, but make it -1, that's the same thing as that. Do you remember that? Reciprocation of a fraction changes the sign of your exponent. If that's to the first power, I can reciprocate those fractions and make it to the negative first power. Yes? I can pull out a negative, I pull out any exponent, right? So I can have a limit of sine x over x, that's 1. 1 to the -1 still gives you back 1. Either way, that's 1. So in our case up here, We could do it that way that I explained earlier. We could break this up as t sine t times t sine t. Each of those is going to give us a limit of 1. Are you with me on that? 1 times 1, our ending limit, this should equal 1. But I want to show you the different way to do this. That's one option. Do you see the option that you can do that? The other option is, well, if you did something similar with that exponent, I could say that this is the limit as t approaches 0. Since the numerator squared and the denominator squared, I can break that exponent out to the top. You with me on that one? Sure? Okay. Also, if I change the sign of that exponent, I can reciprocate my fraction. Do you follow that one? So this says, all right, well, then why don't you just make it limit t approaches 0 of sine t over t. That's something we want. But now, since I reciprocated the fraction, I have it to the negative second power. What we can do with the negative second power is pull that exponent outside of our limit. Now we're home free. Do you need me to recap here a little bit?
Yeah.
Okay, recap. Still get a kick out of that every time. Trig identity, y'all need to know that one. Taking an exponent out. It's very similar to this. If you have x squared over y squared, that is x over y squared. Agreed? Then this is similar to this. If I reciprocate the fractions y over x, then that's just negative 2. That's exactly what I have done here and then there. True? Properties of limits say that if you have a function raised to some power, it's the same thing as a limit of that function raised to that power. So it basically says I can raise the limit to the power instead of raising the function to the power and then taking the limit. So in other words, that's possible. Pull out the exponent, take the limit first, and then do the exponent. You okay with that one? That's the recap. Now, what's the limit as t approaches 0 of sine t over t? So you all agree that's 1, right? What's 1 to the negative second power?
1.
It is just 1. Yeah, anything to 1 to any power gives you 1. So this is going to give you 1. You okay with that one? Well, that was fun. Hey. Any questions on the first one?
Is it only 1 if it's approaching 0, or can it be approaching another number?
That's a good question. If it's approaching any other number besides 0, well then, okay, the only difference on this one for like right here. If it's approaching any other number besides 0, well then sine is actually a number, right? So you can plug that in and be just fine. You wouldn't have to do any of this. The only time it really matters is if the sine of t is 0, which happens at 0 and then pi and then 2 pi again for this example. Here, it wouldn't really matter unless t goes to 0. So that's our situation. So if t's anything else besides 0, you don't even have an issue. Remember I said you should always plug in the number first to make sure you even have an issue? So if this was like going to 1, or, well, let's make it better, pi over 2, you go, let's do pi over 2. Do I need to have a limit identity or anything? No. You just do sine of pi over 2 or pi over 2, and that will actually work out for you. It's going to be 1 over pi over 2 or 2 over pi. So that would be your answer. So you wouldn't have to do any of this stuff if you have a number besides 0. Are you with me on that? It all goes back to you should try your limit before you start doing this is fancy stuff. Try your limit before you do fancy stuff. Plug in the number. If you don't have a problem, then that's your limit. If you do have a problem, then do fancy stuff. Fancy stuff. My fancy hands. Okay, does that answer your question though?
Yeah.
All right, let's try the next one. Now let's practice this then. Are you going to have a problem if you plug in 0? What's the numerator become?
0.
Oh, good, we got that one. What's the denominator become? This is pi over 2, right? Pi over 2 minus 0 is pi over 2, right? What's cosine of pi over 2? I'll give you a hint.
2 over 2?
It starts with a Z and rhymes with hero. It's 0. Yeah, it's 0. You get 0 over 0. That's a problem. So to answer your question again, could you, if that wasn't 0, if it was something else, could you potentially just plug in the number without doing any of this fancy stuff we're about to do? Absolutely. But now that we have 0 over 0, this is where you have to use those limits and identities to get something you know. What's the things you know? You know the limit of sine x over x as x approaches 0 is 1. You know the limit of 1 minus cosine x over x as x approaches 0 is 0. And you know that the limit of tan x over x as x approaches 0 is 1 again. That's the only things you know. So if you can't do the limit directly, you try to make it into one of those things. You follow me on that? Okay, so what can we do? Someone who's really good at identities, tell me what that is.
Something.
I'll take care of the numerator for you. All right, here you go. Bam. Booyah. Do the denominator. What's cosine of 1/2 pi minus x? It's a special little thing. Half angle identity. Yeah. What is it? Oh man, you guys are killing me. You guys are killing me. Know your double angles, your half angles, your Pythagoreans, and the tangent ones. Okay, know what secant, cosecant, cotangent mean, and you'll be okay. Those are the basic ones. Okay, you need to have those down. What this says, if you want to check in the back of your book, cosine of 1/2 pi minus x, or minus your angle, whatever that happens to be, whatever variable you have, that's equal to sine x. That's it. This is sine x. Did that make your problem easier? Much easier, right? If you try messing around with this one, you're like, oh, I have no idea. What's Mr. Leonard going to do there? This is crazy stuff. But that's actually just an identity. Do you know how much this is? Limit of x over sine x as x approaches 0. It is 1. Yes, we actually just talked about that. 1. 1 and done. Cool? Okay, so do you sometimes need some identities to do these problems? Yes, you do. You have to be good at identities in this class. Not a professional, otherwise you'd be teaching, but relatively okay. Okay, you need to at least know them and how to use them. That's why I had you do that identity section, right? So that was a heads up on you should do this. Now, most of you skipped those problems. Don't skip problems. Most of you skipped those problems, but you should have the idea that, yeah, we're going to be using this in class, and it's somewhat helpful unless you just want to spend massive amounts of time banging your head literally against the wall and pulling your hair out. I don't want you to go bald, so learn your identities, and then you can get it a little bit easier. Okay, now, our last one that we're going to do in here, again, I can't give you every example, but I've given you quite a few, I think you'll agree. What can we do with that? What do you think? Any ideas? We did something with 1 minus cosine earlier in the class. Maybe that would work.
Conjugate.
Conjugate it. Yeah, let's conjugate it. Why don't you multiply by the conjugate right now? I'm going to walk you through this one. Multiply by the conjugate of 1 minus cosine theta. Do them both numerator and denominator. Again, what's the conjugate of this that I'm talking about? How do you find the conjugate, basically? Change the sign. Okay, so what is the conjugate specifically for us? Now you got to do it on both the numerator and denominator. You okay so far? We don't necessarily have to distribute the numerator. I'm going to leave that alone in case we absolutely have to later. What I do need to do is distribute the denominator. You follow? So let's try that. So we're going to have the limit. Theta approaches 0. Theta squared. 1 plus cosine theta. Can you tell me how much this is going to give you when you do your distribution? What are you going to get?
1 minus cosine squared theta.
One minus. Hey, we've seen this already. How much is 1 minus cosine squared theta?
Sine squared.
Still okay so far? Are you okay so far with that? Give me a little head nod if you are.
Yeah.
Okay, good. Do you see anything we can do now? What do you think? Do you see anything that looks familiar in this problem? What looks familiar? Maybe that we've done earlier in this class that you could.
Theta squared over sine squared.
Theta squared over sine. You guys see the theta squared over sine squared, right? We just did that. It's right here. We've done that problem. So what I want you to do right now is break that up. I want the theta squared over sine squared times the remaining.
Would that be in 1 minute? 2 seconds?
Well, we'll talk about that in a second. Right now, all I care about is that you see that this right here is going to go together. Do you see it's going to go together? And it's going to be multiplied by 1 plus cosine theta. Do you all have that in your paper right now? Are you seeing how to, if you didn't get that, are you seeing how to get that? Yes, no? It's okay if it's a no, but I need to know it's a no. Is it okay or not? Yeah?
No.
Not so much? This is like this is like over 1, right? If you multiply numerator times numerator and denominator times denominator, it will give you back that thing. Therefore, we can split it up in the opposite manner. Okay, now, what can you do with limits that are being multiplied together? Can you split them up by multiplication? Can you split them up by multiplication? Do that now. Okay, make 2 limits out of it. Limit of this one times the limit of this one. Do that for me. Also, one little piece of information, when you're doing these limits, you have a lot going on, make sure you're putting the parentheses around the argument of your limit, just to make sure that you know I'm taking the limit of this whole thing, not just a limit of 1 and then adding cosine theta. Does that make sense to you? Make sure you see that. Did you make it this far? Okay, now, since we've already proven this, we already know how much this limit is. How much is this limit?
4.
We could redo it if you really want to, right? Pull out the 2, reciprocate it, -2. 1 to the negative second power is still 1. So this thing is 1. Now, can you evaluate this limit at theta equals 0? Is that okay to do now? Sure, you have no denominator. That's fine. Plug in the 0 and do that on your own. Notice how I'm not writing limit anymore. This limit is equal to 1 times this limit is equal to 1 plus cosine of 0, since theta is 0. Notice how you still need parentheses because you're multiplying 1 times something. That's okay. How much is cosine of 0? It is how much?
1.
Cosine of 0 is 1. So what we have in here is 1 plus 1. So 1 times 1 plus 1. What's our limit equal to? Limit is 2. There are a couple different ways you could have done this. You could have broken this up independently, done a few different things. This is probably, in my opinion, the most concise. At least the one I've found that's most concise. So do that, and then we can do any limit. As long as we're finding at least some identities that we've dealt with before inside of our limits and using those things. How many people understood what we talked about so far in our section? How about this, Roy? You guys all right with this? Any questions that we have before we continue? All right, finally done with section 1.2. Whew. Feel good? It's good for me. This thing was long. My goodness.